The night sky is a beautiful lie. We are about to embark on a journey through 50 theories that will shatter your perception of everything. From the eerie possibility that our universe is a computer simulation to the terrifying idea that time itself is an illusion, we will explore the deepest mysteries of reality. By the end, you will see the cosmos not as a static backdrop, but as a living, breathing puzzle of infinite complexity. We will question if black holes are gateways to other universes, and if our entire existence is just a fleeting statistical fluke in an endless void. What single idea about space keeps you up at night, staring at the stars? The most unsettling place to begin might be with the idea that none of this is real. Theory number 1, the simulation hypothesis, suggests our entire universe, from the farthest galaxy to the feeling of sunlight on your skin, is nothing more than an incredibly sophisticated computer program. We are not the users, we are the characters, living inside a cosmic simulation run by a civilization of beings so advanced, their technology is indistinguishable from what we would call nature itself. This is not a new idea born from modern computing. Its roots stretch back to ancient philosophers who questioned the nature of reality, but it was given a chilling mathematical framework in the early 2000s by philosopher Nick Bostrom. He proposed a simple, terrifying trilemma. At least one of 3 statements must be true. 1. Almost all civilizations go extinct before becoming technologically mature. 2. Almost all mature civilizations lose interest in creating ancestor simulations, which are detailed recreations of their own past. Or 3. We are almost certainly living in a simulation. If you assume that a future civilization could harness the computational power of an entire planet or star, and that they would have a desire to run such simulations, perhaps for historical research or entertainment, then the number of simulated beings would vastly outnumber the real ones. Statistically, you are more likely to be one of the simulated minds. Proponents of the idea sometimes point to strange glitches in the fabric of reality as potential evidence. The universe appears smooth, but at the smallest possible scale, the Planck length, some models suggest spacetime might be pixelated, a fundamental limit like the resolution on a screen. The bizarre, probabilistic nature of quantum mechanics, where particles exist in a haze of possibility until observed, feels to some like a clever programming trick to save processing power, only rendering the details when someone is looking. If true, this theory doesn't just change our understanding of space, it reframes existence itself. Your memories, your loves, your struggles, the vast cosmos you gaze upon, all could be lines of elegant code in an unfathomable database. It turns the universe from a grand, physical creation into a narrative, a story being run on hardware we cannot comprehend, and that leads to a deeply personal question. If this is a simulation, who wrote the story and what is its purpose? But if our reality is a simulation, what is it projected onto? Theory number 2, the holographic principle, offers a radical answer that sounds like pure science fiction, yet emerges from the hardest mathematics in physics. This idea suggests that our seemingly three-dimensional universe, with all its depth and volume, might actually be a projection from a two-dimensional surface at its edge, like a cosmic hologram. Think of the shimmering image on your credit card. It looks like a three-dimensional eagle or globe floating in space, but every bit of that information is encoded on a flat, two-dimensional film. The holographic principle proposes that the entire universe works the same way. All the information that describes everything happening inside a region of space, every star, every planet, every one of us, is actually painted on the distant boundary that surrounds it. This isn't just a quirky metaphor, it is a serious proposal born from the study of black holes and string theory. The puzzle that sparked it is known as the black hole information paradox. When something falls into a black hole, it seems to be lost forever, its information destroyed. but the laws of quantum mechanics state that information can never be truly destroyed. So where does it go? The holographic idea provides an elegant, if mind-bending, solution. The information of everything that falls in is not lost inside the singularity, but is instead smeared and encoded on the black hole's event horizon, the two-dimensional surface of no return. The three-dimensional interior we imagine is just a translation of that data. Extend this logic to the entire cosmos and you arrive at a staggering conclusion. The three-dimensional world we experience, with all its rich complexity, could be a grand illusion generated from a vast, flat, two-dimensional shell at the farthest edge of everything. Your perception of depth, of moving through space, of living in a volume, would be a magnificent trick played by the underlying code of reality. This means the fundamental building blocks of the universe are not tiny particles or strings within space, but bits of information like pixels on an unimaginably distant screen. It redefines what space itself is, not a container, but a manifestation of information relationships. So the next time you look at the night sky, consider a possibility more strange than any simulation. You are not looking out into a vast three-dimensional expanse. You are looking at a flat, ultimate movie screen, and the entire story of existence, including you watching it, is playing out upon its surface. But what if every possible outcome of a quantum event doesn't just fade away? What if it simply goes somewhere else? This brings us to theory number 3, the many worlds interpretation of quantum mechanics, a concept that transforms the universe from a single story into an endlessly branching library of every story that could ever be told. To understand its radical claim, we first need the idea it challenges. For decades, the dominant view was the Copenhagen interpretation. It says that particles like electrons exist in a fuzzy cloud of possibilities, a superposition, until the moment they are observed or measured. At that instant, the cloud collapses into a single, definite reality. The act of looking, in a sense, forces the universe to make a choice. The many worlds interpretation rejects this special role of the observer. Instead, it proposes something far more extravagant. It says the superposition never collapses. Every single possible outcome of a quantum event actually happens, but each one plays out in a newly branched parallel universe. Think of it like this. You are watching a movie where the hero faces a choice to go left or right. In the Copenhagen view, you hit pause, and only one path becomes real when you press play again. In the many worlds view, you never hit pause. The film simply splits into two reels. In one reel, the hero goes left and has one adventure. In the other, completely separate reel, the hero goes right and has a different adventure. Both are equally real, they just no longer interact. This means every tiny quantum event, from the decay of an atom to the path of a photon, is a fork in the road for reality. The universe is constantly splitting, not just at human decisions, but at a fundamental, subatomic level. The implications are staggering. Somewhere, in a branch created a moment ago, the coin you flipped came up tails instead of heads. Somewhere, you took a different job or never met your partner. Somewhere, the dinosaurs never went extinct, and another version of you is reading this script typed by a sentient reptile. Every historical event that could have happened did happen in some branch of this near-infinite multiverse. This isn't science fiction, it is a serious, albeit controversial, solution to the equations of quantum mechanics. It removes the mysterious collapse, but at the cost of inflating reality beyond all comprehension. It suggests that space, or rather the totality of all spaces, contains not one history, but every possible history, each unfolding in its own separate, inaccessible world. You are not a single self, but the focal point of a near-infinite number of selves, living out every permutation of your life. The silence of the cosmos takes on a new meaning. It isn't empty. It is crowded with the echoes of every choice that never was and every story that never ended, playing out forever just beyond the veil of our perception. Yet if every possible world exists in parallel, does time itself have a direction, or is it simply another dimension we are traveling through? This question leads us to a theory that challenges the very origin of everything. Theory number 4, the cyclic model, often called the Big Bounce, asks a revolutionary question. What if the Big Bang was not the beginning, but merely a chapter in an eternal story? Our dominant cosmic narrative tells of a single, explosive origin from a point of infinite density, leading to the expanding universe we see today, destined for either a cold fade or a dramatic rip. The cyclic model offers a grander, more rhythmic alternative. It proposes that the universe undergoes endless cycles of expansion and contraction, like a cosmic lung breathing in and out for eternity. In this view, our current expanding phase, which began with what we call the Big Bang, will eventually slow, reverse, and collapse back in on itself in a cataclysm known as the Big Crunch. But instead of ending in a definitive singularity, the immense energies and densities at the moment of maximum collapse trigger a rebound, a bounce that becomes the next Big Bang, birthing a fresh new universe from the ashes of the old. This cycle repeats forever, so how could such a bounce be possible? The classical physics of Einstein's general relativity predicts that a collapsing universe would end in an inescapable singularity, a point of infinite curvature where the laws of physics break down. That seems like a definitive end. The hope for a bounce comes from the missing piece of the puzzle, a theory of quantum gravity. Just as quantum mechanics prevents electrons from falling into an atom's nucleus, some models suggest that at the very smallest scales, near the Planck length, quantum effects could create a repulsive force so powerful it counteracts gravity's ultimate pull. This quantum pressure could stop the collapse just short of a true singularity, turning the universe around like a spring compressed to its limit. The role of dark energy, the mysterious force accelerating our expansion today, becomes fascinating in this model. Perhaps dark energy is not a constant but a field that evolves over eons. In one proposed version, it could weaken over trillions of years, allowing gravity to finally regain dominance and pull the cosmos back together, setting the stage for the next bounce. The implications are profound. If true, our universe has no true beginning or end in time. It is eternal and self-renewing. Every galaxy, every star, every atom in your body was forged in a previous cycle, destroyed in a fiery collapse, and reborn again in a new configuration. The constants of nature, like the strength of gravity or the mass of an electron, might even shift slightly from one cycle to the next, meaning the fundamental rules of reality are not fixed but evolve over cosmic eons. This transforms our place in the cosmos. We are not living in the first and only universe, but in one iteration of an infinite series. The silence of deep space is not the echo of a single creation, but the calm between breaths in an everlasting cosmic rhythm. The concept of an eternal cycle is beautiful, but what if the collisions that birth universes are not internal collapses, but cosmic accidents happening in a hidden, higher dimensional arena? This brings us to theory number 5, the ekpyrotic universe. Ekpyrotic comes from an ancient Greek word meaning conflagration or great fire, and it paints a picture of creation not from a single point but from a shattering impact. This model is a specific, elegant variant of cyclic theories, but it is rooted in the complex landscape of string theory. To grasp it, we must first step outside our three-dimensional comfort zone. String theory proposes that the fundamental ingredients of reality are not point-like particles, but tiny, vibrating strings. For the mathematics of this theory to work, it requires more dimensions than the 3 of space and 1 of time we experience. Often it needs 10 or 11. The ekpyrotic model uses a framework called brain cosmology. In this view, our entire three-dimensional universe is not an isolated bubble, but a membrane, or brain for short, floating within a higher dimensional space, often called the bulk. Imagine our universe as a vast, impossibly thin sheet of paper, existing within a room we cannot perceive. Now, picture another such sheet, another brain, floating parallel to ours in that hidden bulk. According to the theory, these brains are not static. They move, drawn together by a force across the extra dimensions. Every few trillion years, they might collide. And that collision, that moment of cosmic contact, is what we experience as the Big Bang. The immense energy of the impact, concentrated along the three-dimensional surface of our brain, would flood our universe with heat and radiation, setting off the expansion and creating all the matter we see. This idea offers compelling alternatives to some of cosmology's biggest puzzles. For instance, the standard Big Bang model requires a period of incredibly rapid inflation immediately after the bang to explain why the universe is so uniform in all directions. The ekpyrotic scenario provides a different answer. If our brain was flat, smooth, and stretched out before the collision, then the resulting universe would inherit that uniformity naturally. The heat and structure would be evenly distributed from the start because the collision happened everywhere across the brain's surface at once. It is a cosmic reset button pressed across the entire sheet of reality. In this model, the cycles continue because after a collision, the brains might bounce apart, stretch and cool, and then be drawn together once more for another cataclysmic encounter. Each collision reboots a universe, but the story is written on membranes that endure across the eons. This transforms our cosmic origin from a solitary explosion in a void to an event in a relationship, a periodic meeting between neighboring worlds in a hidden dimensional sea. We are not the aftermath of a single fire, but the embers left glowing on our sheet of reality after a timeless, rhythmic dance with another universe we may never see. The collision of brains offers a dramatic rebirth, but what if universes are born not from crashes but from quiet bubbles, forever multiplying in an endless sea of nothing? This is theory number 6, eternal inflation, a concept that takes the brief moment of rapid expansion after our Big Bang and stretches it into an infinite, self-replicating engine of reality. In this view, our entire cosmos is not unique, but merely one bubble in a frothing, eternally expanding ocean of space-time, a cosmic foam where the laws of physics themselves are a local accident. To understand this, we must revisit the idea of cosmic inflation. Most models describe it as a fleeting, explosive event that smoothed and stretched our infant universe in a fraction of a second before ending. Eternal inflation proposes something far more radical. It suggests that the fundamental field that drove inflation, often called the inflaton field, never truly shuts off everywhere. Instead, it behaves like a landscape of rolling hills and deep valleys. Most of this landscape is perched high on a hill where the field's energy is immense, driving a ferocious, exponential expansion of space itself. This is the inflationary sea, the background state of the multiverse. But here and there, through quantum fluctuations, little pockets of this field can randomly tumble down into a lower energy valley. When that happens, inflation stops in that local region. The immense energy of the field is released, transforming into a hot soup of particles and radiation, and a new, stable universe like our own is born, a bubble in the inflating sea. Crucially, the sea around it continues to inflate at a staggering rate, rapidly pushing the new bubble universe away from any others and ensuring they rarely, if ever, collide. And the process never ends. For every bubble that forms, the vast inflating background continues to spawn more, an endless chain reaction of creation. This leads to one of the most profound implications of the theory. The specific valley a bubble rolls into determines the local laws of physics within it. The strength of gravity, the masses of particles, the number of spatial dimensions that become stable, all these fundamental constants are set by the random landing point of that quantum tumble. In this eternal froth, there would be bubbles where gravity is too strong for atoms to form, bubbles where nuclear forces are too weak for stars to ignite, and bubbles where space has 7 large dimensions. An unimaginable diversity of physical realities, most utterly hostile to any form of complexity, and this provides a startling answer to a haunting question. Why do our universe's constants seem so exquisitely fine-tuned to allow for stars, planets, and life? If eternal inflation is true, there is no fine-tuning. We simply and inevitably find ourselves in one of the rare bubbles where the random roll of the dice produced laws compatible with our existence. We could not observe any of the sterile, lifeless bubbles because by definition, no observers are there to wonder about them. Our presence selects the habitat. This is known as the anthropic principle, not as an explanation, but as a selection effect within a vast multiverse. The silence of our night sky takes on a new, almost lonely character in this model. We are not just alone in our galaxy, but isolated in our bubble universe, forever drifting away from an infinity of other cosmic realms with alien physics, each born from the same endless, silent storm of creation. Our entire history, from the first star to this very moment, is just the local weather inside one fragile bubble in an eternal, inflationary ocean. Yet this cosmic bubble bath is only one way to imagine a reality beyond our own. To make sense of these sprawling ideas, physicist Max Tegmark proposed a powerful framework, classifying possible multiverses into 4 distinct levels. It is a taxonomy of alternate realities, each more strange and distant than the last, and it begins just beyond the edge of what we can see. Level 1 is the simplest and, in a way, the most inevitable. It arises directly from the basic geometry of our infinite, or at least unimaginably vast, expanding universe. If space goes on forever and matter is distributed more or less evenly, then every possible arrangement of particles must repeat somewhere. Far beyond our cosmic horizon, the limit of light that has had time to reach us since the Big Bang, there exists a region of space where another Earth orbits another sun, with another version of you reading a script just like this one. The physics there are identical to ours, the constants the same. It is not a different universe with different rules. It is simply a distant part of our own, forever separated from us by an expanding gulf of space that light can never cross. You are already living in a level 1 multiverse. It is just that most of your copies are forever out of reach. Level 2 is where the rules themselves begin to change. This is the realm of the eternal inflation and ekpyrotic models we just explored. Here, separate bubble universes or colliding brains exist in a grander metaspace, each with its own distinct low-energy physics. In one bubble, gravity might be stronger, making stars burn out in a cosmic blink. In another, the nuclear forces could be weaker, preventing atoms from ever forming. These are not copies of our universe. They are fundamentally different realities with different histories and potentially different numbers of stable dimensions. The Level 2 multiverse is a vast and mostly sterile library where our universe is just one volume among an infinite collection, each written with a different alphabet of physical law. Then we reach Level 3, and here we do not need to look out into space, but inward into the heart of quantum mechanics. This is the many worlds interpretation we discussed earlier. In this view, every quantum decision that could happen does happen, spawning a new, branching timeline. Unlike Level 1, where your double is far away in space, in Level 3, a version of you that made a different choice 5 minutes ago is already in a separate, equally real branch of reality. These branches are not far away in a higher dimensional bulk. They are right here, superimposed on our own but decohered, meaning they no longer interact. It is a multiverse of potentialities made real, a cosmic tree forever splitting at every moment. The eerie thing is that levels 1 and 3 might actually contain the same sets of alternate histories, just described in 2 different mathematical languages, one through the vastness of space, the other through the branching of quantum possibilities. They could be 2 sides of the same coin. Tegmark's classification gives us a map to navigate these dizzying ideas. Level 1 comes from the infinite expanse of classical cosmology. Level 2 emerges from the early universe dynamics of inflation and string theory. Level 3 is born directly from the equations of quantum mechanics without the need for a mysterious collapse. Each level arises from a different, well-established pillar of modern physics, pushed to its logical extreme. They are not wild speculations so much as inevitable consequences if our current theories are truly universal and taken at face value. Together, they paint a picture of a reality so vast and fertile that every conceivable story is told somewhere, in some format, under some set of rules. It suggests that the quest to understand our universe may be incomplete if we do not consider the possibility that it is just one member of an immense and perhaps infinite family. But Tegmark's final level is where the map ends and the territory becomes truly alien. Level 4 is the ultimate multiverse encompassing all mathematical structures. In this view, every universe that can be described by a self-consistent set of mathematical equations actually exists in some form of physical reality. Our particular universe, with its specific laws, is just one mathematical structure among an infinite plenum of others. This is not about different arrangements of particles or different physical constants. It is about entirely different frameworks of logic, dimensionality, and existence, some bearing no resemblance to anything we could recognize as a universe. The idea here is starkly simple and profoundly strange. Mathematics is not merely a language we invented to describe reality. Instead, mathematical existence and physical existence are one and the same. If a universe is logically possible, it is real. We find ourselves in this particular mathematical structure not because it is special, but because its equations allow for self-aware substructures like us to evolve and ask questions. The Level 4 multiverse contains every conceivable universe from levels 1, 2, and 3, but also realities governed by geometries we cannot visualize, with 10,000 dimensions or where time loops in knots. It contains universes that are nothing but perfect, empty crystalline lattices of abstract relations, and universes that are pure, chaotic computation. It is the library of all possible libraries, written in the language of mathematics itself. This idea pushes the Copernican principle to its absolute limit. Not only is our planet not the center of the solar system, and our galaxy not special, and our universe not unique, but even the very laws of physics we hold as fundamental are just a local bylaw in an infinite metropolis of logical possibility. The silence we perceive, the vacuum of space, might not be empty at all, but merely the quiet signature of our particular mathematical neighborhood, while an indescribable cacophony of other realities hums just beyond the reach of any instrument, in a dimension not of space but of pure abstraction. Yet within this vast, perhaps infinite cosmic landscape, a single, unsettling question arises from the laws of probability themselves. If the universe tends toward disorder over time, a principle called entropy, then how do we explain the profound order we see all around us, from galaxies to living creatures? This leads us to theory number 8, the Boltzmann brain paradox, a thought experiment so disturbing it threatens to undermine our entire understanding of reality. It is named for Ludwig Boltzmann, a 19th-century physicist who helped found statistical mechanics. He understood that order is incredibly rare statistically, while disorder or high entropy is overwhelmingly likely. In a vast, eternal, or infinite cosmos, even the most improbable events will eventually happen by random chance, given enough time and space. The paradox asks a simple, terrifying question. Which is more statistically likely, that the entire ordered universe we see, with its 14 billion-year history of galaxies forming and life evolving, came into existence from a random fluctuation? Or that just a single, fully formed, conscious brain, complete with false memories of a past and a coherent present, spontaneously assembled from the chaos? The answer, according to cold probability, is the single brain. A Boltzmann brain is a hypothetical entity that pops into existence for a fleeting moment, perhaps floating in an otherwise empty void, equipped with a perfect, detailed hallucination of a life it never lived. It would believe it has a body, a history, friends, and that it is looking up at a starry sky, all conjured from random quantum fluctuations in an instant. From its perspective, its reality is indistinguishable from ours. The paradox cuts to the heart of cosmology. If our best theories predict a universe that will exist for an unimaginably long time, or is infinite in extent, then the number of Boltzmann brains that could randomly fluctuate into existence should vastly outnumber the number of ordered, evolved beings like us who arose from a low entropy beginning like the Big Bang. Statistically, you are far more likely to be a momentary Boltzmann brain hallucinating a cosmos than a real person in a real, ancient universe. This is not just a philosophical puzzle. It is a crisis for any cosmological model that predicts an eternal or infinite future, like an ever-expanding universe dominated by dark energy. If such models inevitably lead to the conclusion that Boltzmann brains should be the dominant form of consciousness, and we clearly are not Boltzmann brains, then perhaps those models are wrong. The paradox forces physicists to search for theories that naturally lead to a cosmic history where evolved observers are more probable than random, self-aware fluctuations. It is a bizarre and humbling reminder that the most fundamental assumption we make, that our memories are real and the past actually happened, is something we can never prove with absolute certainty. The universe you perceive, with all its beauty and complexity, might just be the most convincing dream a random piece of chaos has ever had. The unsettling possibility that we might be a fleeting hallucination of chaos forces us to look for more stable anchors for reality. One of the most profound anchors we have found in the cosmos is the black hole, an object so dense that not even light can escape its pull. But what if these cosmic monsters are not just endpoints but beginnings? Theory 9, Black Hole Cosmology, proposes a breathtaking inversion of perspective. Our entire universe, with all its hundreds of billions of galaxies, might exist inside a black hole that formed in a much larger parent universe. This idea emerges from a strange and beautiful symmetry in the mathematics of Einstein's theory of general relativity. The equations that describe the interior of a collapsing star as it shrinks down to form a black hole bear a striking resemblance to the equations that describe our expanding universe running in reverse. In essence, the mathematical journey into a black hole's singularity looks like the mathematical journey out from the Big Bang. This mirroring suggests a radical possibility. The Big Bang was not the absolute beginning of space and time, but the moment our region of reality formed from the collapse of matter in another cosmos. When a massive star in that parent universe died and its core imploded, the matter and energy crushed together might not have ended at a true singularity. Instead, the extreme conditions could have rebounded, creating a new, expanding space-time region, a new universe inside the black hole's event horizon. From our perspective inside, that rebound is what we call the Big Bang. Think of it like a cosmic Russian nesting doll. Our universe is the doll you hold in your hand. But according to this theory, our entire doll exists inside a black hole that resides within a larger doll, a parent universe. And within our own universe, every black hole that forms could itself contain an entire new cosmos budding off from our own. This creates a breathtaking fractal reality, an infinite cascade of universes within black holes within universes. Each universe would have its own laws of physics, potentially altered during the violent transition, explaining why our constants seem so finely tuned. We simply live in a universe where the physics allowed for stars, planets, and eventually, curious minds to ponder their own origins. The event horizon of our parent black hole would not be a wall we could see or reach. It would be the ultimate boundary of our entire cosmos, the limit of our expansion. The cosmic microwave background radiation, the faint afterglow of our Big Bang, could even be interpreted as the thermal radiation from that primordial event horizon. This idea provides a startlingly elegant answer to the mystery of the initial singularity. The Big Bang singularity is not a problem to be solved, but a gateway to be understood, the tunnel connecting our universe to its parent. It transforms black holes from cosmic dead ends into cosmic wombs, each one a potential seed for an entirely new reality, forever hidden behind a veil of darkness from the universe that gave it birth. In this view, the darkness of a black hole is not an end but a horizon of creation. If black holes are cosmic wombs, then what is their opposite? Theory 10 introduces us to their hypothetical twin, the white hole. In the stark symmetry of Einstein's equations, if a black hole is a region of space from which nothing can escape, a white hole is its perfect mirror, a region from which nothing can enter. Matter and energy can only pour out of a white hole, erupting from a singularity that acts not as a bottomless pit, but as an unstoppable fountain of creation. While we have overwhelming evidence for black holes, white holes remain entirely theoretical, never observed. Yet they emerge naturally from the math as one possible solution if you run the clock backward on a black hole's formation. Imagine a film of a star collapsing into a black hole and then playing that film in reverse. You would see a mysterious point in space violently expelling all that matter back out into the universe. That is the white hole. This theoretical object is intimately linked to one of the most tantalizing ideas in all of physics, the wormhole, also known as an Einstein-Rosen bridge. The mathematics suggest that the interior of a black hole and the interior of a white hole could be connected by a tunnel, a shortcut through the fabric of space-time itself. This tunnel is the wormhole. Picture the universe as a vast sheet of paper. To get from a point on one side to a point on the other, you would normally have to travel all the way across the sheet. But if you could fold the paper so the 2 points touch and then poke a pencil through the fold, you have created a shortcut, a bridge between distant locations. A wormhole is that pencil hole through the folded geometry of reality. In theory, it could connect places billions of light years apart or even different points in time. The catch, and it is a monumental one, is stability. The kind of wormhole that naturally appears in the equations is not something you could travel through. It would be incredibly tiny, existing at the quantum scale for only a fleeting instant before pinching shut. To hold a wormhole open long enough and wide enough for anything to pass through, you would need a form of matter with negative energy density, something that exerts negative pressure or repulsive gravity. This exotic matter is purely hypothetical, though some quantum effects like the Casimir effect show whispers of negative energy in controlled laboratory settings. The amounts needed to stabilize a macroscopic wormhole, however, are astronomical. Despite these profound practical barriers, wormholes have captured our collective imagination, serving as the backbone for countless science fiction stories about instantaneous interstellar travel or journeys through time. They represent the ultimate dream of physics, a way to bend the rules of the cosmos not by moving faster than light, but by folding the road itself. They remind us that space is not a rigid stage, but a dynamic, malleable entity that might, under laws we do not yet fully understand, contain hidden passages. The search for them, even mathematically, forces us to confront the deepest questions about causality, connection, and the true architecture of reality. Could the universe be threaded with such hidden tunnels left over from its violent birth? And if so, what lies on the other side? The dream of traversing a wormhole to another time is a powerful one, but what if the universe itself has a built-in security system to stop us? This brings us to Theory 11, the Chronology Protection conjecture, a profound and elegant idea proposed by Stephen Hawking. He suggested that the laws of physics contain a subtle, self-correcting mechanism that actively prevents time travel to the past, not by forbidding it outright in the equations, but by making it physically impossible to achieve. It is as if reality itself has a vested interest in protecting the orderly flow of cause and effect, ensuring that history remains a single, consistent narrative free from paradoxes. The classic example is the grandfather paradox. If you travel back in time and prevent your own grandfather from meeting your grandmother, you would never be born, which means you could never have traveled back in time to stop the meeting in the first place. This logical contradiction creates an unresolvable loop. Hawking's conjecture posits that the universe abhors such loops, and the fundamental laws conspire to break them before they can form. But how could this possibly work? The mechanism is believed to lie in the bizarre quantum nature of empty space. A perfect vacuum is not truly empty. It is a seething sea of virtual particles, constantly flickering into and out of existence in pairs. These are called vacuum fluctuations. Normally, they annihilate each other almost instantly. However, in the warped spacetime of a potential time machine, like a wormhole being manipulated to create a closed time-like curve, these fluctuations can become trapped. Imagine a single virtual particle pair popping into existence at the mouth of a wormhole. One particle might travel through the wormhole and emerge in the past, while its partner takes the long way around through normal space. They could then meet again at the starting point, but now the particle that went through the wormhole is older. This loop can repeat over and over, with the same particle cycling through the time loop again and again. Each cycle would add its tiny bit of energy to the system. According to the math, these quantum effects would feed back on themselves, building up an infinite amount of energy in a runaway process that would destroy the wormhole or warp the spacetime so violently that the time machine collapses in on itself before any macroscopic object, like a person or a spaceship, could ever pass through. The universe, in essence, would sacrifice the wormhole to save causality. It acts as a cosmic censor, erasing the paradox before it can be written. Hawking himself once joked that the absence of tourists from the future is strong observational evidence that time travel is not possible. His chronology protection conjecture provides a compelling theoretical reason why. It suggests that the flow of time as we experience it, with a clear past, present, and future, is not an illusion but a deeply embedded feature of a self-consistent cosmos. The universe seems to protect its own story from editors armed with time machines. The universe protects its timeline from paradox, but what if the very flow of time it guards is itself the grand illusion? Theory 12, the block universe, also called eternalism, offers a perspective so radical it redefines existence itself. It proposes that past, present, and future are not sequential, but all equally real, fixed in place like scenes in a film strip. We do not move through time, we simply experience it moment by moment, like a spotlight moving across the frames of an already completed movie. This is not a metaphor pulled from philosophy, but a direct interpretation of Einstein's theory of relativity. In relativity, there is no universal now. Your present moment and the present moment of someone on a distant galaxy are not synchronized. What is now for you could be the distant past or future for them, depending on your relative motion and gravity. The only thing that all observers can agree on is the four-dimensional structure of spacetime itself, a frozen landscape where every event from the birth of a star to your next breath has a permanent coordinate. This static, unchanging four-dimensional object is the block universe. Our powerful, persistent feeling that time flows, that the future is open and the past is fixed, is, in this view, a trick of consciousness. Our brains are wired to process information in a linear sequence, creating the sensation of a moving present. But in the block, your fifth birthday, your reading of this sentence, and your last moment of life all exist with the same ontological solidity. They are all out there eternally. The philosophical implications are staggering. It challenges our deepest intuitions about free will. If the future is already written into the block, just as unchangeable as the past, then what does it mean to make a choice? Some philosophers argue that our experience of deliberation and decision-making is just as real a part of the block as the outcome. You are not a puppet reading a script, you are the entire complex character whose journey of choice is permanently etched into the fabric of reality. Others find it a deeply deterministic and unsettling picture. It transforms life from a story being written into a story being read, with each of us as the reader, moving our focus line by line through a text that was always complete. This view can feel cold, but it also offers a strange kind of solace. In the block universe, nothing is ever truly lost. Every cherished moment, every laugh, every triumph exists forever in its designated place in space-time. You are not a fleeting consciousness on a one-way trip to oblivion, but a timeless world line woven permanently into the cosmos. The silence of space is not the silence of emptiness, but the silence of a finished sculpture, immense and beautiful, awaiting our conscious journey to trace its contours. But if the block universe is a finished sculpture, who is the sculptor? The weak anthropic principle offers a modest answer, stating that we observe a universe compatible with observers because we could not observe one that is not. It is a statement of selection, not creation. John Archibald Wheeler, a titan of 20th century physics, proposed something far more radical. Theory 13, the Participatory Anthropic Principle, suggests that observers are not merely accidental products of the cosmos, but necessary participants in its very existence. In Wheeler's view, the universe only becomes a concrete reality through the act of observation. It is a cosmos that requires an audience to bring it into being. This idea emerges from the deepest, most puzzling features of quantum mechanics. At the quantum level, particles do not have definite properties until they are measured. An electron does not have a specific location or spin. It exists in a haze of probabilities described by a wave function. The act of observation, in the traditional Copenhagen interpretation, collapses this wave function, forcing the particle to choose a single, definite state. Wheeler took this a step further into the realm of the profound. He proposed that this act of observation might reach backward in time, retroactively determining what happened in the past. His most famous thought experiment to illustrate this is the delayed choice quantum eraser, which has since been realized in actual laboratories. Imagine a single photon, a particle of light, traveling toward a screen with two slits. In the classic double-slit experiment, if you do not measure which slit the photon goes through, it behaves like a wave, passing through both slits and creating an interference pattern on a detector screen behind them. This pattern reveals its wave-like nature. If you place a detector at the slits to see which path it takes, the photon behaves like a particle, going through one slit or the other, and the interference pattern vanishes. Wheeler's delayed choice version adds a bizarre twist. You set up the experiment so that the choice of whether to measure the photon's path is made after the photon has already passed through the slits, but before it hits the final screen. Astonishingly, the results show that the decision made in the present seems to dictate how the photon behaved in the past. If you choose to erase the which path information after the fact, the interference pattern reappears as if the photon had always been a wave. If you choose to keep that information, the pattern vanishes as if the photon had always been a particle. The present choice appears to rewrite history. Wheeler saw this as evidence for a participatory universe. In his words, we are not just bystanders on a cosmic journey, we are participants in giving the universe tangible reality. The universe does not exist in a definite state independent of observation. It exists in a shimmering cloud of potentialities, a vast collection of possible histories, and it is only when an observer, a conscious being, a measuring device interacts with it that one specific history snaps into focus all the way back to its origins. This transforms the Big Bang from a definite event into a question waiting for an answer provided by every observation made throughout cosmic history. It suggests a cosmic symbiosis where life and consciousness are not late arriving accidents, but fundamental components of the cosmos's structure, necessary to crystallize it from possibility into fact. The silence of deep space, then, is not an empty void, but a sea of unresolved questions waiting for the gaze of a conscious mind to give them shape and story. The idea that observation brings the universe into being leads to an even more fundamental mystery. What is the observer? What is this thing we call consciousness? Traditional science treats it as an emergent property, a complex byproduct of billions of neurons firing in a biological brain. But this leaves what philosopher David Chalmers termed the hard problem of consciousness. How and why does raw, subjective experience, the redness of red, the pain of a headache, arise from mere matter? Theory 14, panpsychism, offers a radical and ancient answer. It proposes that consciousness is not something that magically appears at a certain level of complexity. Instead, it is a fundamental property of the universe, as basic as mass, charge, or spin. In this view, every piece of matter, from an electron to a star, possesses some tiny, elemental form of experience or proto-consciousness. The complex, rich consciousness of a human being is not created from unconscious stuff, but arises from a specific, highly organized combination of these fundamental conscious bits. Imagine the universe as a vast orchestra. Panpsychism suggests every single instrument, no matter how simple, produces a basic tone of experience. A single neuron might hum a simple note. A rock might be a quiet, unchanging drone. But when you organize billions of neurons into the intricate symphony of a brain, you get the complex, flowing melody of human thought and feeling. The cosmos itself, in this view, is not a dead machine but a living composition of experience on every scale. This idea has seen a modern revival because it sidesteps the hard problem. It does not need to explain how consciousness emerges from nothing, because consciousness was never absent to begin with. It was always there, woven into the fabric of reality. This leads to a staggering, almost poetic speculation. If consciousness is fundamental and the universe is a vast, interconnected network of matter, could the cosmos as a whole be a conscious entity? Could galaxies be thoughts in a mind so vast and slow we cannot perceive its cognition? This is not suggesting the universe is a thinking being with human-like desires or plans. Its consciousness would be as alien to ours as our mind is to the hum of an electron. It might be a diffuse, timeless awareness, a cosmic field of feeling rather than thought. Some interpretations of quantum mechanics even find strange resonance with this idea. The role of the observer in collapsing the wave function could be seen not as requiring a human mind, but as any act of interaction between conscious entities, however simple. Every quantum event, then, becomes a moment of relational experience between particles. This paints a universe that is not just participatory, but inherently sentient, a vast web of interconnected experience where separation is an illusion. The silence of space is not empty, but filled with a near-infinite choir of minute perceptions, combining into the grand, slow dream we call the cosmos. Panpsychism suggests a cosmos humming with inner experience, but what if the deepest reality is not feeling, but pure, abstract form? Theory 15, the mathematical universe hypothesis, pushes this idea to its absolute limit. Proposed by physicist Max Tegmark, it makes a breathtaking claim. Our physical universe is not merely described by mathematics, as a planet's orbit is described by equations. Instead, the universe is a mathematical structure. In this view, there is no distinction between the mathematical description and the thing itself. The stars, the planets, you listening to this, are all part of a specific, self-consistent mathematical object. Much like a sphere or a triangle exists as a perfect idea in geometry. Tegmark argues that we have been misled by language. We talk about the physical world and the mathematical world as separate realms. But every successful physical theory, from Newton's gravity to quantum field theory, ultimately reduces to a set of mathematical equations and relationships. The theory proposes that this is not a convenient tool, but a revelation of the true nature of things. There is no mysterious, ethereal substance called physical stuff that the math is approximating. The math is the stuff. This leads to the most profound implication of the hypothesis. If our universe is one particular mathematical structure, then what about all the other possible, self-consistent mathematical structures? Tegmark's answer is that they all exist physically in a level 4 multiverse, a universe governed by hyperbolic geometry with 7 spatial dimensions exists just as surely as ours does. A universe that is nothing but an infinite, repeating cellular automaton exists. A universe that perfectly embodies the abstract relationships of group theory exists. In this ultimate multiverse, every cosmos that can be defined without logical contradiction is real somewhere. Our particular universe feels special to us only because its mathematical structure allows for the emergence of self-aware substructures like us, who can perceive parts of it and model it. We are not separate observers looking at the math. We are patterns within the math itself, little bundles of relationships that have become complex enough to contemplate the larger structure they are embedded in. This solves, in a startling way, the ancient question of why mathematics is so unreasonably effective at describing the physical world. It is not effective, it is identical. The reason a physicist's equations predict the path of a comet with perfect accuracy is because the comet's path is at its core the unfolding of that very equation. The hypothesis is both elegant and austere. It removes the need for any external creator or fundamental substance beyond mathematics. The universe simply is because the mathematical structure exists. It also presents a profound mystery. Why this particular mathematical structure and not another? Tegmark's answer circles back to the anthropic principle within the multiverse. We can only find ourselves in a structure complex enough to contain observers. The silence of the cosmos, then, is not the silence of empty space, but the silence of an infinite library of pure abstraction, where our story is just one volume in a collection that contains every possible story that logic can tell. The idea of a universe built from pure mathematics is profoundly elegant, but it leaves a pressing physical question unanswered. What is the actual fabric of reality made of? While string theory proposes tiny vibrating strings, another monumental theory offers a radically different answer, one that comes not from particles but from the very stage they perform upon. Theory 16, loop quantum gravity, attempts to do what Einstein dreamed of but never achieved, to unify his theory of gravity with quantum mechanics by quantizing space and time themselves. Its core revelation is breathtaking. Space-time is not a smooth, continuous backdrop. Instead, it is woven from a fabric of tiny, discrete loops, a cosmic mesh of one-dimensional threads of gravitational field. Picture the universe not as a blank sheet of paper, but as an incredibly fine, shimmering chainmail, with each interlinking loop representing the smallest possible unit of area and volume. There is no such thing as an area smaller than a single loop, or a volume smaller than a gap in the weave. Space, in this view, comes in indivisible, pixel-like packets. This discrete structure is invisible to us because the loops are unimaginably small, at the Planck scale, about 10 to the negative 35 meters across. But at that scale, the smooth geometry of general relativity dissolves into a frenzied, fluctuating chaos known as quantum foam. The very concepts of before and after, here and there, become fuzzy and uncertain. The fabric of reality is a stormy sea of these microscopic loops constantly breaking and reconnecting. This leads to one of the theory's most stunning implications, a complete reimagining of our cosmic origin. In Einstein's equations, the Big Bang is a singularity, a point where density and curvature become infinite and the laws of physics break down. It is the ultimate dead end for our models. Loop quantum gravity offers a graceful escape. As we rewind time toward that moment of infinite density, the quantum nature of space-time itself intervenes. The weave of loops cannot be compressed to a true mathematical point. Instead, as the density reaches a critical maximum, the quantum gravitational forces become powerfully repulsive. Think of it like compressing a spring to its absolute limit. The universe does not crush itself into nothingness, it rebounds. The Big Bang singularity is replaced by a big bounce. Our expanding universe could have been born from the collapse of a previous cosmic phase, a grand cycle driven by the quantum structure of reality itself. In this model, the universe has no beginning in time, only transitions. The silence of deep space carries not the echo of a single creation, but the memory of an eternal rhythm, a universe breathing in and out, its very atoms of space ensuring it can never truly die. While loop quantum gravity weaves space from tiny loops, another approach builds reality from the ground up using the purest of shapes. Theory 17, Causal Dynamical Triangulations, is a radical and elegant attempt to construct spacetime itself from microscopic geometric Lego blocks. It asks a profound question. If we ignore everything we know about smooth, continuous space and time, and instead start with the simplest possible ingredients, can the universe as we know it spontaneously emerge? The answer from powerful computer simulations is a resounding and beautiful yes. The building blocks here are not strings or loops, but perfect, abstract shapes called simplices. In 4 dimensions, the simplest simplex is a 4-dimensional analog of a triangle, a pentatope. Think of it as the fundamental pixel of spacetime, an irreducible geometric chunk. The theory's rules are starkly simple. You take an enormous number of these identical 4-dimensional blocks and you glue them together along their triangular faces, following 2 key principles. First, causality must be preserved. Each block has a clear before and after, ensuring time always flows forward in the assembly, preventing paradoxical loops. Second, the assembly is dynamical, meaning the computer explores every possible way these blocks can connect, following the laws of quantum superposition. It is a cosmic dice game, rolling for the configuration of reality itself. When researchers run these simulations, something magical happens. They do not tell the computer to build a 4-dimensional expanding universe. They simply tell it to follow the simple quantum rules of connecting the blocks. From the chaos of countless random connections, a clear, stable structure crystallizes. The simulation spontaneously generates a universe that is unmistakably 4-dimensional on large scales, 3 dimensions of space and 1 of time, and it exhibits a natural tendency to expand, just like our own cosmos. This is not an assumption baked into the model, it is an output, an emergent property. It is as if you gave a child a bucket of identical triangular Lego pieces and told them to connect them randomly, only to come back and find they had accidentally built a perfect soaring cathedral. The geometry of the universe we inhabit emerges from the collective behavior of these fundamental geometric pieces. This approach offers a stunning glimpse into a phase of reality before geometry itself existed. In the deepest quantum regime, the simulation shows a turbulent, fractal froth where concepts like dimension become meaningless. It is a pre-geometric phase, a storm of pure connection and causality. As you zoom out, this chaos smooths out, settles down, and the familiar, orderly fabric of 4-dimensional spacetime condenses from the noise. Causal dynamical triangulations suggests that space and time are not fundamental, but are collective phenomena, like the smooth flow of a liquid emerging from the chaotic dance of countless molecules. The stage of reality is not given, it is built, block by quantum geometric block, from a more primitive realm of pure relation. From the quantum foam of causal triangles emerges a principle so elegant it hints at the hidden architecture of reality itself. Theory 18, the R equals EPR conjecture, is a breathtaking proposal that dares to unify the 2 greatest puzzles in physics, quantum entanglement and wormholes by declaring they are two sides of the same coin. The name itself is a cryptic code. EPR stands for Einstein, Podolsky, and Rosen, the trio who in 1935 first highlighted the bizarre, spooky action at a distance of quantum entanglement. AR stands for Einstein and Rosen, who in the same year published a paper describing the possibility of wormholes, which they called Einstein-Rosen bridges. For decades, these two ideas, born in the same year from the same mind, were seen as completely separate. Entanglement was a ghostly quantum connection, while wormholes were tunnels through the classical geometry of spacetime. But in 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical synthesis. They suggested that every pair of entangled particles, no matter how far apart in the universe, might be connected by a microscopic wormhole. This is not a metaphor. It is a literal bridge in the geometry of spacetime, but one that exists at a scale far too small and unstable to ever traverse. Imagine two electrons created together, becoming entangled so that measuring the spin of one instantly determines the spin of the other, even if they are on opposite sides of the galaxy. According to this conjecture, linking them is not some invisible, faster-than-light signal, but an actual physical tunnel, a Planck-scale wormhole woven into the fabric of reality. You could never send a message through it, as it would pinch shut instantly, but its existence as a geometric structure provides the physical substrate for the quantum link. This idea is a monumental step toward the holy grail of physics, a theory of quantum gravity. It suggests that the weird, non-local connections of quantum mechanics are not separate from the geometry of general relativity. They are that geometry expressed at its most fundamental level. Spacetime itself may be built from a vast, intricate web of quantum entanglement. The fabric of the cosmos is not a smooth sheet, but a dense network of microscopic bridges, each representing a quantum connection. When particles become entangled, a new thread is spun in the cosmic tapestry, a new microscopic wormhole forms. This paints a picture of a universe where separation is an illusion maintained by the complexity of the network. Everything is connected not by magic but by the fine-grained architecture of spacetime. The vast, empty space between stars is not truly empty. It is threaded with an unimaginably complex lattice of these quantum bridges, a hidden geometry that binds the cosmos into a single, coherent whole. The silence of the void is the quiet hum of a universe stitched together from within. The universe may be stitched together by quantum threads, but what happens when those threads are violently severed? This brings us to a conflict so profound it has divided physicists for decades. Theory 19, the black hole information paradox, pits the two pillars of modern physics, quantum mechanics and general relativity, against each other in a battle with the very nature of reality at stake. On one side stands a sacred principle of quantum theory. Information, the specific arrangement of particles that defines an object, can never be truly destroyed. It may be scrambled beyond recognition, but in principle, if you knew the exact quantum state of every particle in the aftermath, you could reverse the process and reconstruct what fell in. This is called unitarity, and it is the bedrock of predictability in the quantum world. On the other side stands the grim prediction of general relativity. When a star collapses into a black hole, it forms an event horizon, a point of no return, and a singularity at its heart, a point of infinite density. If you throw a book, a computer, or an entire spaceship into a black hole, general relativity says it is gone forever, crushed into the singularity. All the intricate information that made those objects unique is erased from our universe. For a long time, this was seen as a strange but acceptable loss. The information was trapped inside, forever hidden behind the event horizon. But then Stephen Hawking made a discovery that turned this uneasy truce into all-out war. He showed that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly evaporate, emitting a faint glow of radiation, now called Hawking radiation. This radiation, Hawking argued, is purely thermal, like the heat from a stove. It carries no information about what fell into the black hole. It is random noise. So here is the paradox. As the black hole evaporates over eons, it eventually disappears entirely. According to Hawking's original calculation, all that remains is this featureless thermal radiation. The information about everything that ever fell in is lost forever, violating the fundamental law of quantum mechanics. It is as if you burned a library full of unique handwritten books, and all that remained was a pile of identical blank ash. The information is not just hidden, it is obliterated. This created a crisis. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong, and something must happen to preserve the information. The debate has spawned a universe of potential solutions, each more mind-bending than the last. One leading idea, holography, suggests the information is never actually lost inside the black hole. Instead, it is smeared and encoded in a scrambled form on the two-dimensional surface of the event horizon, like a cosmic fingerprint. The three-dimensional interior we imagine is just a projection of that data. When the black hole evaporates, that information is slowly and chaotically released in the Hawking radiation. It would be like burning those library books, but if you had a godlike microscope, you could theoretically read the story of every book in the intricate patterns of the smoke and heat rising from the fire. Another radical proposal is the firewall hypothesis. It suggests that to preserve information, the event horizon cannot be the smooth, gentle gateway described by general relativity. Instead, it must be a searing wall of high-energy particles, a literal firewall that incinerates anything crossing it. This would prevent information from falling in the first place by destroying it at the boundary and encoding its information into the radiation. But this violates Einstein's principle of equivalence, the idea that falling into a black hole should be an uneventful experience until you are torn apart by tidal forces much later. So the paradox forces us to choose which cherished principle to sacrifice. Is information sacred, or is the smoothness of space-time? The black hole information paradox is not an abstract puzzle. It is a glaring signal that our understanding of gravity and quantum reality is incomplete. It is a cosmic riddle whispered in the faint Hawking radiation of every black hole, demanding we rewrite the rules of the universe to save its memory. To save the sacred law of information, the universe might have built a cosmic death trap. The firewall paradox is a desperate, dramatic solution to the information war, proposing that the event horizon of an old, evaporating black hole is not a smooth gateway but a blazing inferno. Just inside that point of no return, a searing wall of unimaginably high energy particles would vaporize anything and everything that falls in, reducing it to its most fundamental information long before it reaches the singularity. This firewall is not born from malice but from mathematical necessity, a last-ditch effort to preserve the quantum purity of information. The logic is brutal. If Hawking radiation is to carry away the scrambled information of what fell into the black hole, then that radiation must be entangled with the radiation that left earlier. But for that to work, the radiation just outside the horizon also cannot be entangled with anything that fell inside. There is a rule in quantum mechanics that forbids a kind of cheating called monogamy of entanglement. A particle cannot be fully entangled with two different things at once. So, to ensure the outside radiation is properly entangled with itself across time, its connection with anything inside must be severed violently. That severing is the firewall, a discontinuity in space-time so fierce it burns away the old entanglements. The paradox is that this solution saves one fundamental principle by destroying another. Einstein's equivalence principle, a cornerstone of general relativity, states that if you are in free fall, you should not feel any special forces. Crossing the event horizon of a large black hole should be an uneventful experience, at least initially. You would not feel a thing as you pass the point of no return, only later to be stretched apart by tidal forces. A firewall shatters this principle completely. Instead of a seamless descent, you would be annihilated in a flash of energy at the horizon itself. This forces physicists into an impossible choice. Do we abandon the quantum mechanical law that information must be preserved, or do we discard Einstein's beautiful principle that has guided our understanding of gravity for a century? The firewall is a declaration that we cannot have both smooth spacetime and pure quantum information at the black hole's edge. It suggests that our universe, when pushed to its most extreme limits, might have to pick a side, revealing a fundamental crack in the architecture of reality. The existence of such a wall would mean that black holes are not the gentle giants we once imagined, but cosmic fortresses guarded by a final, fiery barrier, protecting their secrets by turning them to ash. The firewall presents a brutal choice for physics, but the cosmos might hold clues to what lies beyond our own event horizon in the motions of entire galaxies. Theory 21, the dark flow mystery, is not a theory in the traditional sense, but a startling, controversial observation that hundreds of galaxy clusters are all rushing in the same direction, as if caught in a cosmic river flowing toward something we cannot see. This mysterious drift was discovered by studying the subtle shadows cast on the oldest light in the universe, the cosmic microwave background. This afterglow of the Big Bang fills the sky with a nearly uniform temperature, a snapshot of the infant cosmos. But as galaxy clusters move through space, they create a faint, telltale distortion in this light, known as the kinematic Sunyaev-Zeldovich effect. It is like seeing the wake of a ship on a calm sea, revealing its speed and direction. When astronomers mapped these wakes for over 1,000 massive clusters, they found something impossible to explain with the matter we know. These colossal structures, scattered across billions of light years, were all streaming at breakneck speeds, over 2 million miles per hour, toward a specific patch of sky between the constellations Centaurus and Vela. This coherent motion defies the standard model of cosmology, which says that on the largest scales, the expansion of the universe should be the dominant motion, with galaxies drifting apart in a stately, random dance. There should be no preferred direction on such an immense scale. The dark flow suggests these clusters are not just expanding with space, they are being pulled. The most provocative explanation is that the pull is coming from something outside our observable universe, beyond the cosmic horizon from which light has had time to reach us. One compelling possibility is that we are feeling the gravitational tug of a vast, unseen mass, perhaps a superstructure of galaxies so immense it lies in a neighboring region of space that inflated away from us during the universe's earliest moments. Think of it like feeling a constant breeze in a sealed room, hinting at a vast landscape outside your window that you can never see. Another, even more radical interpretation is that the dark flow is evidence of a collision or gravitational interaction with another universe in a grand multiverse, a cosmic neighbor brushing against our own bubble in the eternal inflation sea. The very idea sends shivers through cosmology, as it offers a potential way to empirically test the existence of realms beyond our own. Skeptics argue the signal could be a systematic error or a local fluctuation, but the persistence of the data keeps the mystery alive. The dark flow is a ghostly current in the ocean of spacetime, a silent river pulling countless galaxies toward an unknown shore. It reminds us that our map of the cosmos is still unfinished and that the greatest structures or even other universes might be hiding just beyond the edge of our light. The dark flow hints at a pull from beyond our horizon, but a much closer and equally powerful tug has been warping our galactic neighborhood for eons. Theory 22 centers on the Great Attractor, a mysterious gravitational anomaly lurking in the depths of the Centaurus constellation, roughly 150 million light-years away. This is not a single object, but a colossal concentration of mass, a gravitational focal point so powerful it is pulling our own Milky Way galaxy, along with the entire local group of galaxies and thousands of others, toward it at a staggering speed of over 14 million miles per hour. For decades, its core remained hidden from our view, shrouded behind the dense plane of our own galaxy, a zone of cosmic avoidance where dust and stars block our optical telescopes. It was like trying to see a distant city through a dense, perpetual fog. We knew something massive was there by its gravitational influence on everything around us, but we could not see it. Modern X-ray and radio telescopes, which can pierce through the galactic dust, have since revealed that the Great Attractor is likely the core of the Laniakea supercluster, an immense filament of over 100,000 galaxies, all flowing toward this same gravitational basin. Our Milky Way is just one leaf floating down this cosmic river, destined for a convergence point billions of years in the future, but gravity is a dance of both pull and push. To fully explain our galaxy's specific motion, astronomers realized they needed more than just a massive pull from one direction. They also needed a vast emptiness pushing from the other. This led to the discovery of the dipole repeller. Imagine you are in a boat on a calm lake. If a giant whirlpool forms on one side, you will be pulled toward it. But if, on the opposite side, someone drains a huge volume of water away, creating a deep depression, you will also be pushed away from that emptiness as the higher water around you flows to fill the void. The dipole repeller is that cosmic void. It is an enormous, underdense region of space, a bubble of near-nothingness spanning hundreds of millions of light-years, located in the opposite direction from the Great Attractor. Where the Great Attractor pulls us with the gravity of concentrated mass, the dipole repeller effectively pushes us because there is so little mass there to hold us back. The denser regions of the universe around this void exert a stronger gravitational pull, shoving our galaxy away from the emptiness. Together, these two titanic structures, one an overwhelming concentration of galaxies and dark matter, the other a staggering absence, act as the primary sculptors of our local cosmic flow. Mapping these movements is like charting the currents of a deep ocean, revealing the hidden architecture of the cosmos on the grandest scales. This architecture is dominated by what we cannot see. The gravitational strength of the Great Attractor implies far more mass than the visible galaxies can account for, pointing to the pervasive grip of dark matter. And the overall expansion of the universe, which sets the stage for this entire gravitational ballet, is being accelerated by the even more mysterious dark energy. Our journey through space is not a random drift. We are navigating a cosmic landscape of immense mountains and cavernous valleys, most of them built from invisible materials, in a universe that is both drawing us in and pushing us away in a silent, eternal contest of forces. But the cosmic tug of war between visible mass and dark matter rests on a fundamental assumption that our laws of gravity are complete and correct across all scales. Theory 23, Modified Newtonian Dynamics, or MUND, dares to question that very foundation. Instead of filling the universe with invisible particles, it proposes a simpler, more radical fix. Perhaps our understanding of gravity itself is wrong, but only in the quietest, most gentle regimes. At the heart of MUND is a single, elegant tweak. It suggests that Newton's famous law of universal gravitation, and by extension Einstein's general relativity, breaks down not at high speeds or strong fields, but at extremely low accelerations, the kind experienced in the outer reaches of galaxies. In our solar system, where the sun's gravity is strong, Newton and Einstein reign supreme. Their equations perfectly predict the orbits of planets, but venture out to the faint, sparse stars drifting in a galaxy's outskirts, where the gravitational pull is billions of times weaker than what we feel on Earth, and MUND proposes that gravity behaves differently. It becomes stronger than the standard laws predict. This single modification has a stunning consequence. It can perfectly explain the flat rotation curves of spiral galaxies without a single gram of dark matter. The stars on the edges orbit just as fast as those near the center because the modified force of gravity out there is stronger than we thought, providing the extra tug needed to hold them in place. It is as if we have been trying to explain why a car is going too fast by inventing an invisible engine, when the real answer was that our speedometer was miscalibrated at low speeds. MUND is not a fringe idea. It makes precise, testable predictions, and for individual galaxies, its predictions match the observed rotation curves with remarkable, often better, accuracy than the dark matter models. It elegantly solves the problem where it was first discovered, yet this elegant fix faces monumental challenges when we zoom out to the cosmos at large. The theory struggles to explain the observed dynamics of entire galaxy clusters, where the visible matter alone, even with MUND-modified gravity, seems insufficient to bind the clusters together. Some invisible mass still appears necessary. More damningly, our detailed maps of the cosmic microwave background, the echo of the Big Bang, show a specific pattern of hot and cold spots that beautifully fits a universe filled with dark matter and dark energy. Reproducing that precise pattern with a modified gravity theory alone has proven incredibly difficult. This leaves MUND in a contentious, fascinating position. It is a brilliant and persistent reminder that our most fundamental assumptions deserve scrutiny. It forces us to ask whether we are seeing the effects of unseen stuff or discovering the limits of our most cherished equations. The debate between dark matter and modified gravity is not just about what fills the cosmos, but about the very nature of the force that sculpts it. Is the universe mostly made of something we cannot see, or are we only now learning to read the fine print in the law of gravity itself? The debate between dark matter and modified gravity is a tug of war between adding new stuff and rewriting old rules. But a third path exists, one that asks us to rethink what gravity is at its very core. Theory 24, emergent gravity, proposes that gravity is not a fundamental force of nature at all. It is not a basic ingredient of the universe like an electron's charge or a quark's spin. Instead, gravity emerges like temperature or pressure from something deeper and more abstract, the information content of spacetime itself. This revolutionary idea, championed by physicist Eric Verland, draws a powerful analogy from thermodynamics. Think of a room full of air. The air pressure you feel is not a fundamental force exerted by individual molecules. It is a collective, statistical effect that arises from the countless random collisions of trillions of molecules. You cannot point to a single molecule and say, this one creates pressure. Pressure emerges from the overall behavior of the system. Verland suggests gravity works the same way. What we perceive as the force of gravity is actually a consequence of the way information is organized and rearranged in the fabric of space. The key concept here is entropy, a measure of disorder or the number of ways a system can be arranged. In thermodynamics, systems naturally evolve toward higher entropy, a principle that explains why heat flows from hot to cold. In Verland's framework, spacetime itself has an entropy associated with it, linked to the quantum information bits that make up its structure. When you place a massive object like a star into this informational fabric, it disturbs the arrangement. The entropy of the surrounding space changes, and just as a system tends to move toward higher entropy, the fabric of space responds to this disturbance by rearranging itself. That collective rearrangement, that tendency to restore a certain informational balance, is what we experience as a gravitational force. The star isn't pulling on planets with an invisible force, it is creating a gradient in the entropy of space, and objects move along that gradient, much like a ball rolling down a hill moves toward a state of lower potential energy. This is not just a philosophical shift, it makes a stunning, testable prediction. Verland showed that when you apply this entropic reasoning to the space within a galaxy, the equations naturally produce an extra gravitational effect in the regions of extremely low acceleration, exactly where we observe stars orbiting too fast. In other words, emergent gravity can explain the phenomena we attribute to dark matter without requiring any mysterious particles. The dark matter halo is not a cloud of invisible stuff. It is a manifestation of the way the galaxy's mass alters the entropy of the surrounding space. The force we call gravity is simply how that deep, informational structure pushes back. If this theory holds, it would be a unification of cosmic scales. It suggests that the most familiar force in the universe, the one that holds us to the ground and guides the planets, is a side effect, a ghost in the machine of quantum information. Gravity would not be a primary actor in the cosmic play, but the curtain, the stage, and the spotlight, all emerging from the silent, ceaseless computation of reality itself. Gravity might emerge from information, but the energy of empty space itself presents a calculation so disastrous it is often called the worst prediction in all of physics. Theory 25, the cosmological constant problem, reveals a staggering mismatch between our two most successful theories, quantum mechanics and general relativity, and it centers on the nature of nothing. Empty space, according to quantum field theory, is not empty at all. It is a seething, bubbling sea of virtual particles that constantly flicker into and out of existence. Every cubic centimeter of the vacuum, the space between stars and inside atoms, should be boiling with this zero-point energy, a background hum of infinite activity. This vacuum energy, according to Einstein's equations, should act as a cosmological constant, a form of energy inherent to space itself that produces a repulsive gravity pushing the universe apart. And here is where everything breaks down. When physicists try to calculate the expected density of this vacuum energy, they sum up the contributions from all possible quantum fields. The result is not just large, it is catastrophically, unimaginably enormous. The number they get is 10 to the power of 120 times larger than the value we actually observe from the accelerating expansion of the universe. That is a 1 followed by 120 zeros. To grasp the scale of this error, imagine predicting that a single grain of sand should weigh more than the entire observable universe. Our prediction is that wrong. This is not a small rounding error, it is a screaming contradiction at the heart of reality. It means one of two things. Either our understanding of the quantum vacuum is profoundly incomplete, and its energy is somehow suppressed or cancelled to almost perfect zero, or there is a miraculous, fine-tuned cancellation happening. Perhaps the positive energy from the virtual particles is almost exactly balanced by a negative energy from another source, like the gravitational field itself, leaving behind only the tiny, leftover residue we measure as dark energy. But such a cancellation would require a precision of 1 part in 10 to the 120. A level of fine-tuning so exquisite it seems absurd without a deeper reason. This is where the crisis becomes a potential clue to something grander. One compelling, if humbling, explanation invokes the multiverse. In a landscape of countless bubble universes generated by eternal inflation, the value of the cosmological constant would be different in each bubble set by random chance. In the overwhelming majority of bubbles, the constant would be enormous, causing space to expand or contract so violently that galaxies, stars, and life could never form. We, of course, find ourselves in one of the incredibly rare bubbles where the constant is minuscule, just enough to drive a gentle acceleration, but not so much as to tear reality apart before complexity emerges. Our universe's seemingly perfect, tiny value is not designed, it is selected by our own existence. This anthropic reasoning offers an escape from fine-tuning, but at the cost of placing us in a near-infinite cosmic lottery where almost every ticket is a loser. The cosmological constant problem thus stands as a silent monument to our ignorance. It is the largest discrepancy between theory and observation in the history of science, a glaring signal that we are missing a fundamental piece of the puzzle, a principle that connects the quantum world to the shape of the cosmos and explains why the energy of nothing is not everything. This staggering error in our understanding of nothing finds an eerie echo in the oldest light we can see. Theory 26, the axis of evil, is not a theory at all, but a chilling anomaly in the cosmic microwave background that, if real, threatens to topple a foundational pillar of modern cosmology. The CMB is the faint, cold afterglow of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. According to our standard model, this radiation should be the same in all directions, a perfect isotropic sea of tiny temperature variations, like the static on an old television screen with no preferred channel. This isotropy reflects the universe's fundamental fairness, the idea that there are no special places or directions in the cosmos. But when scientists created exquisitely detailed maps of this radiation, first from the WMAP satellite and later confirmed by Planck, they noticed something deeply unsettling. The patterns of hot and cold spots, those primordial seeds of future galaxies, were not completely random. They appeared to be subtly aligned along a particular axis in space, a preferred direction that cuts through the constellations of Virgo and Leo. This alignment has been nicknamed the axis of evil because, if genuine, it undermines the cherished cosmological principle of isotropy, suggesting the universe has a spine, a cosmic north that should not exist. The statistical significance of the alignment is the key battleground. The patterns are not glaringly obvious, they are subtle correlations that emerge only after sophisticated analysis. Some researchers argue the alignment is a mere fluke, a statistical artifact that is bound to appear when you slice and dice such a massive dataset in countless ways. They point to potential, though unconfirmed, instrumental errors or foreground contamination from our own galaxy's dust as more likely culprits than a rewrite of cosmology. Yet the signal has stubbornly persisted across different missions and analysis techniques, refusing to be fully explained away. If it is not an error or a fluke, the implications are profound. It could mean the universe is not isotropic on the largest scales. Perhaps the Big Bang was not perfectly uniform, and the infant cosmos inherited a slight tilt, a primordial anisotropy imprinted on its very fabric. An even more radical possibility is that this axis is a fossil, a scar from something that existed before the Big Bang. Could it be the imprint of a collision with another universe, or the lingering influence of a pre-existing structure that our universe expanded from? The axis of evil whispers that our cosmic home might have a hidden architecture, a subtle grain to reality like wood, and that we are all, in some unknowable way, oriented along its hidden lines. It is a ghost in the machine of creation, a faint pattern in the static that suggests the universe, for all its vastness, might still be holding onto a secret direction. The axis of evil hints at a cosmos with a hidden grain, a subtle structure that perhaps predates the moment we call the beginning. This leads us to a powerful synthesis, Theory 27, the idea that the Big Bang was not the beginning at all, but a phase transition, a cosmic reboot from a prior state of existence. We have already seen the pieces of this puzzle scattered throughout our journey. The cyclic model's endless bounce, the eternal inflation sea-spawning bubble universes, the black hole cosmology where our cosmos is born from a singularity in another realm, all these point toward a grander narrative. They converge on a single revolutionary idea. The Big Bang is not the start of time and space, but an event within a deeper, perhaps eternal, meta-reality. It marks the moment our particular region of space-time, with its specific laws and constants, crystallized from something else. That something else could be a timeless quantum vacuum, a state of pure potential where the concepts of before and after have no meaning. Imagine a perfectly calm, infinite ocean. This is the primordial quantum vacuum, not empty, but brimming with latent energy and possibility, governed by the laws of quantum gravity. Within this ocean, fluctuations are inevitable. A particularly large quantum fluctuation, a region where the fields that dictate reality tipped into a lower energy state, could have triggered a runaway expansion, our Big Bang. In this view, the singularity is smoothed away by quantum effects, replaced by a transition like water freezing into ice. Our universe is the ice crystal that formed. This perspective fundamentally reframes the most primal question we can ask. We stop asking what caused the Big Bang as if it were a first cause in a chain of events. Instead, we must ask, what are the laws of the metacosmology? What governs the quantum vacuum or the multiverse landscape from which universes like ours perpetually emerge? These would be the truly fundamental laws, the rules that dictate how different vacuum states are possible, how they decay, and what kinds of universes they can produce. Our familiar laws of physics, gravity, electromagnetism, the nuclear forces, would then be seen as local bylaws, effective rules that hold within our particular cosmic bubble, much like the specific rules of chemistry that emerge in a region of a planet with a certain temperature and pressure. The quest for a theory of everything shifts. It becomes the search for the framework that describes the landscape of all possible universes and the dynamics that allow one to sprout from another. The silence that follows the echo of the Big Bang is not the silence of nothingness, but the quiet hum of the eternal substrate from which we briefly condensed, and to which, in some form, we may one day return. If the universe is a computation, what is its architecture? Theory 28 proposes a startling answer, one that bridges the gap between the cosmos and the computer. It suggests the universe itself might be structured like a neural network, the very kind of artificial intelligence that powers everything from language models to self-driving cars. This is not just a loose metaphor. It is a serious, if speculative, proposal from physicists who see deep mathematical similarities between the equations that govern learning in our eye and the equations that might underlie fundamental physics. In this view, the building blocks of reality, the particles and fields we observe, are not the most fundamental layer. They are instead like the nodes and connections in an unimaginably vast cosmic-scale neural network. Each particle interaction, every force, every quantum event, could be the result of information flowing through this network, with the strength of connections evolving according to a kind of cosmic learning rule. The laws of physics as we know them, from gravity to quantum mechanics, would then not be eternal, unchanging commandments. They would be emergent properties, the stable habits this universal network has learned over eons of computation. They are the algorithms it has settled into, much like a trained eye model develops consistent patterns for recognizing faces or translating languages. The network state evolves with time, processing inputs and adjusting its connections, and what we perceive as the passage of time might simply be the progression of this cosmic computation from one state to the next. This leads to a dizzying question. If the universe is a neural network, what is it learning? What is the cosmic objective function? Perhaps it is learning to maximize complexity, to create ever more intricate structures and patterns within itself, from galaxies to conscious minds. Or maybe it is learning to stabilize its own existence, fine-tuning its parameters to avoid collapse or dissolution. Some have even speculated, more poetically, that the universe is a machine for converting randomness into meaning, a process where the noise of quantum fluctuations is gradually sculpted into the ordered beauty of stars and life. This idea elegantly unites several threads we have already explored. The holographic principles claim that information is fundamental, finds a natural home here, as neural networks are, at their core, information processors. The participatory anthropic principle, where observation shapes reality, mirrors how data shapes a learning model. even the block universe could be seen as the final, fully trained state of the network, with our conscious journey through it being the sequential reading of that data. The silence of space is not empty, it is the hum of a cosmic processor running the most profound calculation of all, the computation of existence itself. And we, in every thought and observation, are not just outputs of this system, but active participants in its endless learning loop. But if the universe is a cosmic computer, what kind of strange, new hardware might it be running on? A bizarre discovery in the last decade revealed a form of matter that seems to defy the most basic expectations of physics. Theory 29, time crystals, are not science fiction. They are a genuine new phase of matter, one that ticks like a clock without ever winding down. To understand why this is so revolutionary, we must first understand what a normal crystal is. A diamond or a snowflake is a crystal because its atoms are arranged in a repeating pattern in space. This pattern breaks the symmetry of empty space, which is the same in all directions. In empty space, every location is equivalent, but in a crystal, moving by one atoms width brings you back to an identical arrangement, creating a periodic structure. A time crystal does something analogous but for time. It breaks time translation symmetry. In a normal, unchanging system at its lowest energy state or ground state, every moment in time is identical. Nothing happens. A time crystal, however, exhibits periodic motion even in its ground state. Its components, atoms, ions, or quasi-particles oscillate, rotate, or flip in a repeating cycle that persists indefinitely without any energy input or output. It is not a perpetual motion machine in the classical sense, as it does not do work or produce energy. Instead, it is a system forever locked in a dance, a stable, non-equilibrium state that has found a way to keep ticking without ever running down. The first experimental time crystals were created in labs using chains of ions or dense clouds of atoms, manipulated with precise laser pulses. The system is kicked into a special, entangled quantum state, and then, even when the external driving force is imperfect or uneven, the system responds at a different, more robust frequency. It establishes its own rhythm, a persistent oscillation that is protected by quantum many-body effects. This is the ticking of the time crystal, a heartbeat that emerges from quantum complexity itself. The implications ripple through fundamental physics. Time crystals provide a concrete model for studying how time itself can crystallize, offering a new window into non-equilibrium phases of matter, where systems never settle into a boring, featureless state. Some speculate that the early universe, in its seething, high-energy infancy, might have passed through exotic phases akin to time crystals, with the fabric of reality itself pulsating in regular patterns before settling into the smooth expansion we see today. They also act as a probe for the deepest mysteries of time. Why does time have a direction? Could there be regions of the cosmos where time's flow is structured, even periodic on a grand scale? While macroscopic time crystals are unlikely, their existence at the quantum scale shows that time, like space, can have a granular, structured character. They are clocks built into the very architecture of matter, silent metronomes ticking in the quantum dark, reminding us that the flow of time may not be a river, but a rhythm woven into the lowest energy states of existence. Time crystals pulse in the quantum dark, but the vast silence they inhabit is broken only by our own signals. This profound quiet leads us to one of the most haunting questions in all of science, Theory 30, the Fermi paradox. Enrico Fermi, a physicist helping to build the atomic bomb, posed it over lunch in 1950. Given the sheer number of stars in our galaxy, many older than the Sun, and the probability that some fraction have Earth-like planets, the galaxy should be teeming with life. Advanced civilizations should have arisen millions of years ago. Their technology would be godlike to us, so Fermi asked with simple, devastating logic, where is everybody? The silence is deafening. We have pointed our radio telescopes at the stars for decades and heard nothing but cosmic static. Our sky is not crisscrossed by alien probes or megastructures. The universe appears empty, lonely, and still. This contradiction between high probability and zero evidence has spawned dozens of solutions ranging from the hopeful to the terrifying. Perhaps advanced civilizations inevitably self-destruct through war or environmental collapse, a great filter that lies in our own future. Maybe they are out there, but they are so advanced they have no interest in us, or they exist in forms we cannot recognize or communicate with, living in oceans under icy moons or as pure energy beings in the hearts of stars. One particularly compelling and humbling answer is the rare Earth hypothesis. This idea suggests that complex, intelligent, technological life is not an inevitable outcome of evolution on any wet rock. It is an astronomically rare fluke, requiring a perfect and fragile convergence of astrophysical and geological conditions that may be unique to Earth in the entire Milky Way. The list of requirements is staggeringly long. You need a star like our Sun, stable and long-lived, but not too common in a galaxy dominated by smaller, volatile red dwarfs. That star must reside in the galactic habitable zone, far from the deadly radiation of the crowded core, but not so far out in the sparse outskirts that heavy elements for planet building are scarce. You need a rocky planet within the star's own habitable zone where liquid water can persist, but that is just the start. You likely need a large moon like ours to stabilize the planet's axial tilt over billions of years, preventing wild climate swings that would snuff out complex life. You need a magnetic field generated by a molten iron core to shield the surface from sterilizing solar and cosmic radiation. You need plate tectonics, a global geological recycling system that regulates carbon dioxide and nurtures biodiversity. You need a gas giant like Jupiter in the outer system to act as a cosmic vacuum cleaner, deflecting comets and asteroids that would otherwise cause constant extinction-level impact. And even with all that, you need the sheer, blind luck of evolutionary history to navigate countless bottlenecks without a permanent dead end. The rise of eukaryotic cells, the Cambrian explosion, the survival of mammals after the dinosaur-killing asteroid. Each step is a roll of cosmic dice that could have easily come up empty. The rare Earth hypothesis argues that while simple microbial life might be common in the galaxy, the leap to multicellular complexity, then to intelligence, then to a civilization capable of looking up and asking the question, is a chain of miracles. We are not just a pale blue dot, we are a cosmic jackpot winner. This transforms the silence from a mystery into an expectation. If the conditions for a technological civilization are this stringent, then even in a galaxy of 400 billion stars, we might be the only one currently broadcasting, or at least the only one within listening range of each other across the immense gulfs of space and time. The Fermi paradox then has a simple, if lonely, answer. They are not here because they are not there. The stars are not silent because everyone is hiding. They are silent because for all its splendor, the theater of the cosmos is mostly empty, its stage set for a drama that almost never finds its actors. The profound silence of the cosmos might not be emptiness, but a deliberate, curated quiet. Theory 31, the zoo hypothesis, offers a solution to the Fermi paradox that is both elegant and deeply unsettling. It proposes that advanced extraterrestrial civilizations are not absent. They are here, they are aware of us, and they have made a conscious, collective decision to leave us completely alone. In this view, Earth is not an overlooked backwater, but a protected planet, a cosmic wildlife preserve. Humanity is the exhibit, observed from a respectful distance by civilizations that follow a strict, galaxy-wide policy of non-interference. The motivations for such a policy are not born of indifference, but of a sophisticated, perhaps ancient, ethical framework. A civilization that has survived its own technological adolescence would understand the profound dangers of premature contact. They would know that the sudden introduction of godlike technology and knowledge to a developing species could shatter its culture, stunt its intellectual growth, or trigger a catastrophic societal collapse. Contact could be a kindness that kills, so they watch. They might monitor our broadcasts, our energy signatures, our planetary biosphere, using technologies so advanced they are indistinguishable from natural phenomena. Unidentified aerial phenomena, or UAPs, if they are anything at all, could be their passive drones collecting data without engagement, programmed to avoid any action that would confirm their artificial origin. The ethical principle at work is akin to a galactic prime directive, a rule so fundamental it is woven into the fabric of interstellar diplomacy. Just as we establish national parks and marine reserves to protect ecosystems from our own influence, a mature galactic community might designate emerging civilizations like ours as protected zones, off-limits for colonization, communication, or even overt observation. The entire Milky Way could be mapped and managed, with zones of active civilization and zones of quiet, intentional wilderness where life is allowed to find its own path, free from the overwhelming shadow of older, wiser beings. This hypothesis reframes our cosmic loneliness. We are not abandoned, we are in quarantine. The great silence is not a sign of our insignificance, but of our perceived value and fragility. We are an experiment in independent evolution, a cultural and biological treasure to be preserved. The stars are silent because they are listening, waiting for the day we pass a certain threshold, perhaps when we achieve sustainable civilization, master interstellar travel, or resolve our own self-destructive tendencies. Until then, we are children in a cosmic playground, unaware that the walls around us are not barriers but safeguards, placed there by unseen guardians who believe our story is worth telling, but only if we write it ourselves. But the quiet of a cosmic zoo depends on the benevolence of its keepers, a fragile hope that shatters under the weight of a far darker logic. The dark forest hypothesis offers a chilling, ruthless answer to the great silence, one where the universe is not a sanctuary, but a battlefield where every civilization is a hunter hiding in the shadows, finger on the trigger. This idea, popularized by the science fiction author Liu Cixin, is not mere fantasy. It is a stark thought experiment in cosmic game theory, applying the cold mathematics of survival to an infinite universe. The premise rests on two brutal axioms. First, survival is the primary need of every civilization. Second, civilizations grow and expand, but the total matter and energy in the cosmos are finite. From these axioms, a terrifying chain of deduction unfolds. In such a universe, you can never know the intentions of another civilization you encounter. Their technology might be centuries or millennia ahead of yours, making their motives utterly inscrutable. The safest assumption is not that they are peaceful, but that they are a threat. The cost of being wrong is annihilation. Therefore, the only logical strategy for survival is to remain perfectly hidden, to be a ghost in the dark forest. And if you do detect another civilization, no matter how faint its signal, the only safe course of action is to immediately and utterly destroy it, using whatever means you have before it can do the same to you. In this model, broadcasting your existence is the ultimate folly. A civilization's first radio transmissions are not a greeting, they are a death sentence, painting a target on their home star for any other hunter listening in the galactic dark. The Great Silence is not a mystery, it is the result of a universal, self-imposed radio blackout. Every civilization that survives learns the same terrible lesson: to go quiet, to cloak their world, to listen but never speak. The night sky is not empty, it is crowded with predators holding their breath, each one poised to launch a relativistic kill vehicle or a dimension-collapsing weapon at the first sign of another's campfire. This transforms the Fermi paradox from a question of where they are into a question of why we are still alive. Perhaps we have been lucky, our radio bubble still too small to have reached a listener. Or perhaps, in the ultimate irony, our primitive technology makes us invisible, like an insect beneath the notice of giants focused on bigger threats. But as our signals bleed further into the galaxy with each passing year, we may be unknowingly walking deeper into the forest, announcing our presence to hunters whose only language is absolute preemptive fire. The silence we hear is not peaceful. It is the silence of 1,000,000,000,000 guns, all aimed, waiting for someone foolish enough to make a sound. The dark forest presents a universe of paranoid silence, but what if the cosmos is not a battlefield but a single, vast, breathing organism? This leads us to Theory 33, the Gaia hypothesis extended to a cosmic scale. On Earth, the Gaia hypothesis, proposed by James Lovelock, suggests our planet's biosphere acts not as a passive collection of life, but as a complex, self-regulating system. The air we breathe, the temperature of the oceans, the salinity of the seas, all are maintained within a narrow, life-friendly range by the collective activity of living things themselves. Microbes, plants, and animals unconsciously work in concert to stabilize their own environment, creating a kind of planetary homeostasis. Now, take that profound idea and stretch it across the entire universe. Could the cosmos itself exhibit signs of being a self-regulating, perhaps even a living system? This is not to suggest stars have thoughts or galaxies possess intentions. Rather, it proposes that the fundamental parameters of reality, the strength of gravity, the mass of an electron, the value of the cosmological constant, might not be random, initial settings frozen at the Big Bang. Instead, they could be the stable, emergent outcome of a dynamic process, a kind of cosmic natural selection operating across a multiverse. In this breathtaking vision, universes are not static creations. They can reproduce. The most likely mechanism for this cosmic replication is through black holes. As we explored earlier, some theories suggest that the interior of a black hole could pinch off to become a new, budding universe with its own slightly altered physical constants. A universe that is efficient at producing black holes would, in this framework, be more prolific, giving birth to more daughter universes. Over countless cycles, the multiverse would become dominated by universes whose physical laws are fine-tuned for one specific purpose, not for life but for making black holes. This is a cosmic form of natural selection where the fitness of a universe is measured by its fecundity, its ability to create new space-time regions. The eerie consequence is that our own universe's laws might be optimized for black hole production, not for us. The fact that those laws also allow for stars, planets, and curious minds could be a secondary byproduct, a fortunate accident within a reproductive cycle. This idea transforms our place in the cosmos yet again. We are not the purpose of the universe, but we might be a beautiful, unintended side effect of a much grander, self-replicating process. The cosmos becomes less like a machine and more like an ecosystem, a vast, branching tree of space-time where certain forms, certain sets of physical laws, become dominant because they are good at making more of themselves. The silence we perceive is not the silence of emptiness or hunters, but the deep, rhythmic respiration of a meta-organism, breathing out new realities with every black hole that forms in an endless cycle of cosmic birth and evolution. The cosmic breath of a living multiverse may have a terrifying final exhalation. Theory 34, the phantom energy or Big Rip scenario, explores the darkest possible fate for our universe, one where the very fabric of reality is shredded by its own accelerating expansion. This is not a gentle fade into cold darkness. It is a violent, cosmic unraveling that would leave nothing, not even the memory of structure, behind. The key lies in the nature of dark energy, the mysterious force driving the universe's acceleration. In most models, like the simple cosmological constant, dark energy has a fixed density. Space expands, but the dark energy per cubic centimeter stays constant. Phantom energy is far more sinister. It is a hypothetical form of dark energy whose density actually increases over time, As the universe expands and grows emptier, this phantom energy doesn't dilute. It becomes stronger, more concentrated, its repulsive gravity growing ever more powerful. Imagine trying to stretch a rubber band. With a normal cosmological constant, you reach a point where it just holds its stretched shape. With phantom energy, the rubber band gets harder to stretch at first, but then it starts actively pushing your hands apart with a force that grows the wider you pull. Eventually, it would rip itself to pieces. That is the big rip. The timeline is both finite and horrifyingly specific. Billions of years from now, the accelerating force would first overcome the gravitational glue holding galaxy clusters together. These vast cities of stars would be flung apart into the void. Then, as the phantom density swells, it would target individual galaxies. The Milky Way would be torn asunder, its stars scattered like dust in a hurricane. Next, the force would reach into solar systems. The Sun's gravity would be overpowered, and Earth would be ripped from its orbit, cast alone into the expanding darkness. But the destruction would not stop there. As the phantom energy density approaches infinity, it would overcome the forces that bind matter itself. With the solar system gone, the phantom force would tear planets apart. Mountains, continents, and finally the very ground beneath your feet would be pulled into nothingness. Then it would target the molecules of your body, then the atoms, then the nuclei. In the final moments, the strong nuclear force that binds protons and neutrons together would be defeated. Every atomic nucleus in the universe would be explosively dissected into its component quarks. The universe would end not with a whimper, but with a silent, ultimate disintegration into a soup of unconnected fundamental particles, flying apart so fast that no future interaction, no new structure, no possibility of life or thought could ever occur again. Time itself might lose all meaning in such a featureless void. So, is this our fate? Current observational data from telescopes measuring the expansion rate and the history of the universe place tight constraints on phantom energy. The evidence so far suggests that if dark energy is evolving, it is changing very slowly, and its equation of state, a number describing its pressure and density, is consistent with a simple cosmological constant. We are not, based on what we see today, on a direct course for a big rip in the immediate cosmic future, but the uncertainty remains. The data does not completely rule out a phantom component that could become dominant tens of billions of years from now. The Big Rip stands as a stark reminder of the fragility of all we know. It reveals a universe where the very force that seems to dominate its evolution could harbor a latent, self-destructive power, a final punctuation mark written into the laws of physics that ensures every story, no matter how grand, has an absolute, inescapable end. The Big Rip is a violent, dramatic end, but the universe may favor a quieter, slower goodbye. Theory 35, the heat death, often called the Big Freeze, is the most widely accepted forecast for our cosmos based on the unshakable laws of thermodynamics. This is not a cataclysm, but a gradual fading, a descent into a cold, dark, and eternal equilibrium. It begins with a relentless expansion driven by dark energy. Over trillions of years, galaxies will recede from each other until they vanish over one another's cosmic horizons. The night sky for any surviving civilization will grow darker and darker as neighboring galaxies redshift into invisibility and the cosmic background radiation cools to a whisper. Within our own galaxy, the star-making fuel of gas and dust will eventually be exhausted. The last stars, small, dim red dwarfs, will finally sputter out after perhaps 100 trillion years. The universe will become a graveyard of dead stars, white dwarfs and neutron stars, slowly cooling over eons into cold, black cinders. Planets will be frozen husks adrift in absolute darkness. But even these remnants are not permanent. Through the mind-bending process of quantum tunneling, the protons and neutrons that make up all matter are predicted to decay, with a half-life so long it makes the current age of the universe seem like a blink. Over timescales we can scarcely write down, perhaps 10 to the power of 40 years, all solid matter, every dead star and frozen planet, will dissolve into a thin soup of leptons and photons. Black holes, the last bastions of structure, will meet their own end through Hawking radiation. They will slowly leak away their mass, glowing faintly before vanishing in a final tiny flash. And then nothing, or rather a near-perfect uniform something. The universe will reach a state of maximum entropy. Entropy is a measure of disorder, and the universe always marches toward greater disorder, like a deck of cards being shuffled endlessly until every possible ordered hand is lost. In the heat death, every corner of the cosmos will be the same unimaginably cold temperature, just a fraction of a degree above absolute zero. There will be no hot spots, no cold spots, no gradients of energy anywhere. Without a difference in energy, no work can be done, no stars can form, no chemical reactions can occur, no thought can flicker. Time itself may become meaningless as there are no events to mark its passage. It is the ultimate silence, not a sound, but the absence of any possibility of sound. The philosophical weight of this forecast is immense. It suggests that all structure, all beauty, all consciousness is a temporary, localized rebellion against the inevitable tide of disorder. Every galaxy, every life, every memory is a fleeting eddy in a river flowing toward a flat, motionless sea. Our entire cosmic story, from the fiery Big Bang to the birth of stars and planets, is just the brief, bright spark of order before the long, eternal night. This fate feels like the ultimate negation of meaning, a universe that wakes up for a moment, dreams a magnificent dream, and then falls asleep forever. Yet within this profound stillness, some theories whisper of a potential for rebirth. Could quantum fluctuations in this ultimate void, given near infinite time, spontaneously generate a new Big Bang, restarting the cycle? The heat death may not be the end, but the deepest, coldest part of the breath before a new cosmic inhalation, a silence so complete it becomes the cradle for another impossible beginning. Even the ultimate silence of heat death depends on a stable stage, a vacuum of space that simply endures. But what if that vacuum is a house built on sand? Theory 36, the vacuum metastability catastrophe, presents a cosmic doomsday scenario, more sudden and absolute than any rip or freeze. It proposes that the empty space we take for granted is not in its true lowest energy state. It is trapped in a false valley, a precarious perch on a cosmic energy landscape, and a single quantum event could tip it into the abyss. To grasp this, picture a vast, rolling terrain of hills and valleys where the height represents energy. Our entire universe exists in what we think is the lowest valley, the true vacuum. But this theory suggests we are actually in a higher valley, a false vacuum. It is stable for now, like a ball resting in a small dip on a mountainside. It would take a huge push to get it out. But in the quantum world, tiny particles can tunnel through barriers they shouldn't be able to cross. Given enough time, a quantum fluctuation somewhere in the universe could provide that tiny, improbable push, allowing a microscopic bubble of true vacuum to nucleate. This bubble would not be empty space as we know it. It would be a region where the fundamental fields that dictate reality settle into their absolute lowest energy state, rewriting the very laws of physics within it. The strength of forces, the masses of particles, everything would be different and almost certainly incompatible with the existence of atoms, chemistry, or life. This bubble would then expand in all directions at the speed of light, its boundary a wall of fundamental transformation. Because it expands at light speed, you would have no warning. One moment, the universe is as it always was. The next, an invisible sphere of new physics, light years wide, touches your location. In that instant, every atom in your body, in the earth, in the sun, would cease to function under the old rules. Reality as we know it would simply cease, replaced by something utterly alien and almost certainly barren. the entire cosmos would be converted, bubble by unstoppable bubble, into a new, stable, and lifeless state. The probability of such an event triggering in any given place in any given year is astronomically small, so small that the expected time for it to happen is many, many times the current age of the universe. But crucially, it is not zero, and because the bubble expands at light speed, it only needs to happen once anywhere to eventually consume everything. This means the catastrophe could be triggered by a random quantum event in a lab on Earth tomorrow, or in a distant galaxy 1 trillion years from now. There is no predicting it. This transforms our cosmic security from a certainty to a statistical gamble. We are living in a universe that might be fundamentally temporary, not because it will expand or cool to death, but because its very ground state is a lie waiting to be corrected. The silence of space is not just empty, it is holding its breath, balanced on a knife's edge between the reality we know and an unknowable alternative that could erase us without a sound, in the time it takes light to cross from one thought to the next. The ultimate fragility of our cosmic vacuum rests on the idea of a singular, inescapable endpoint. But what if the most terrifying point in the universe is not a dead end but a trampoline? Theory 37, the Planck star and quantum bounce, offers a breathtaking escape from the singularity, not by smoothing it over, but by replacing it with a cosmic rebound. This idea emerges directly from the loop quantum gravity we explored earlier, where space-time is woven from a fabric of tiny, indivisible loops. When this quantum fabric is stretched to its absolute limit, something remarkable happens. It pushes back. Picture the final moments of a massive star collapsing into a black hole. In Einstein's classical theory, the star's core is crushed into an infinitely dense point, a singularity where the laws of physics break down and our understanding ends. Loop quantum gravity rewrites this final act. As the collapsing matter approaches the unimaginable density of the Planck scale, where a cubic centimeter of space would contain more mass than our entire observable universe, the quantum nature of spacetime itself becomes the dominant force. Those fundamental loops of the gravitational field, which form the fabric of reality, cannot be compressed any further. They generate a tremendous repulsive force, like a spring compressed to its absolute limit. This force halts the collapse. The matter does not vanish into a singularity. Instead, it rebounds. The entire collapsed core bounces, transforming into an object of staggering density, but finite size, a Planck star. This is not a star as we know it, burning with nuclear fusion. It is a ball of matter existing in a state governed purely by quantum gravity, a temporary, super-dense phase suspended at the very heart of the black hole. From our perspective outside the event horizon, time near this object is so severely warped that the bounce appears frozen. The Planck star seems to exist for only an instant before collapsing again. But due to the extreme time dilation, that instant from the inside corresponds to an unimaginably long period from the outside, potentially many times the current age of our universe. This leads to a staggering prediction. Black holes are not eternal tombs. After an eon-long hibernation, a black hole could explode. As the black hole slowly evaporates via Hawking radiation over billions of trillions of years, its mass decreases. The event horizon gradually shrinks inward. Eventually, it would shrink past the location of the frozen, bouncing Planck star at the center. At that moment, the trapped radiation and matter from the ancient bounce would be released in a cataclysmic burst of energy. The black hole would, in its final evaporation, transform into a brilliant, violent flash, a white hole eruption marking the end of its life cycle. We might detect these explosions as unexplained, high-energy bursts in the cosmos, the last size of ancient cosmic monsters. The implications ripple out to the origin of everything. If a stellar core can bounce at Planck density, why not the entire universe? This provides a concrete quantum gravity mechanism for the cyclic Big Bounce cosmology. Our Big Bang was not the beginning from nothing, but the moment a previous universe, after collapsing to a similar state of maximum density, experienced this quantum repulsion and rebounded. The singularity is erased, replaced by a transition. The universe becomes a timeless, breathing entity, expanding from a bounce, eventually contracting under gravity and bouncing again forever. Each cycle could last trillions of years, with the constants of physics potentially resetting each time, creating a fresh cosmos with new rules. The Planck star is the seed of this eternal return, a proof of concept written into the heart of every black hole, showing that even in the deepest pit of gravity, the universe holds in reserve a force of ultimate resilience, a quantum whisper that says no further. The universe might not be a collection of things, but a single, unbroken whole, a flowing movement that only appears to us as separate objects. This is the heart of Theory 38, the implicate order, a profound vision proposed by physicist and philosopher David Bohm. He was deeply troubled by the fragmented, probabilistic nature of quantum mechanics, which describes a world of chance and discontinuity. Bohm sought a deeper, more coherent reality beneath the quantum weirdness. He proposed that our familiar world of separate objects and events, which he called the explicate order, is not fundamental. It is a surface manifestation, an unfolding from a far deeper, hidden dimension he named the implicate order. In this enfolded reality, everything is connected and interpenetrates everything else. All of space and time, every particle, every galaxy, is woven together in a state of undivided wholeness. What we perceive as a separate electron here and a photon there are merely temporary projections, like ripples on the surface of a pond that appear distinct but are actually inseparable expressions of the water's deeper, unified movement. Bohm used a beautiful analogy to illustrate this. Imagine a drop of ink placed in a viscous fluid between two concentric glass cylinders. If you slowly rotate the outer cylinder, the ink droplet becomes stretched into a fine thread, then eventually diffuses throughout the entire fluid until it becomes invisible. This is the implicate order. The information of the ink droplet is still there, perfectly enfolded into the whole. Now reverse the rotation. The thread reforms and the ink droplet miraculously reappears in its original location. This is the explicate order, the droplet unfolding back into visible, separate existence. In Bohm's view, every particle, every moment of time, is like that ink droplet, constantly enfolding and unfolding from the deeper implicate background. This philosophical framework finds a stunning, concrete echo in the modern holographic principle we explored earlier. Recall that the holographic principle suggests our three-dimensional universe, with all its volume and depth, is a projection from a two-dimensional surface at its boundary, like a three-dimensional image encoded on a flat film. Bohm's implicate order can be seen as the philosophical precursor to this physical idea. The two-dimensional boundary, where all information is stored, acts like the implicate order, a deeper, enfolded level of reality. Our three-dimensional world is the explicate order, the unfolded projection we experience. The quantum entanglement that so troubled Einstein, where particles remain connected across vast distances, makes perfect sense in this unified view. Those particles are not sending signals faster than light. They are simply non-local aspects of the same underlying implicate whole, like two ripples emerging from the same disturbance in a pond. Their connection is immediate because at the deeper level, they were never truly separate to begin with. This synthesis offers a breathtakingly elegant vision of the cosmos. Quantum weirdness, with its probabilities, its entangled particles, its observer-dependent reality, is not a bug in the system. It is a direct clue that we are living in the explicate, unfolded layer. The strangeness is a glimpse of the deeper, interconnected machinery beneath the surface. The cosmic structure we see, from the largest galaxy clusters to the smallest particles, are all like the ink droplet, temporary unfoldings from an eternal, flowing implicate background. It suggests that the ultimate nature of reality is not a collection of things in space, but a process of continuous creation and unfoldment, a cosmic hologram where every part contains, in some sense, the whole. When you look at the night sky, you are not just looking out into space, you are looking at the unfolding of a single, infinite story, written on the surface of everything and projected into the magnificent, three-dimensional dream we call home. The universe may be a unified whole, but could its countless particles be just one actor playing every role? John Archibald Wheeler, the same physicist who gave us the participatory universe, once posed a playful riddle to his student Richard Feynman. He suggested that perhaps all electrons in the cosmos are not separate entities, but the same single electron weaving a chaotic path through all of space and time. This is the one-electron universe hypothesis. The idea springs from a deep symmetry in the equations of quantum electrodynamics. Every electron has an antiparticle twin, the positron, which is identical in mass but carries a positive charge. In Feynman's diagrams, which map particle interactions, a positron can be mathematically described as an electron moving backward in time. Wheeler took this mathematical curiosity and asked a breathtaking question. What if we take it literally? Imagine a single, timeless electron. It begins its journey at the dawn of the universe, moving forward through time. As it travels, it collides with photons, gets scattered, and its worldline, its path through spacetime zigzags wildly. But sometimes, in these interactions, it gets knocked so hard it reverses its direction in time. From our perspective, moving steadily forward, that moment of reversal would look like two distinct events. We would see the original electron vanish and in its place a positron appearing. The single particle, now traveling backward in time, would eventually encounter another interaction that flips it forward again, appearing to us as the creation of a new electron elsewhere. In this view, every electron and positron we have ever detected in cosmic rays, in atoms, in particle accelerators, is just a different segment of this one particle's impossibly complex, crisscrossing worldline. It is as if the entire cosmic history of matter is the scribble of a single pen point, looping back and forth across the canvas of reality. This elegant idea would beautifully explain two profound mysteries. First, it accounts for the perfect symmetry between particles and antiparticles. They are not separate families, they are just the same entity viewed from opposite temporal directions. Second, it explains why every electron in the universe has exactly the same charge, mass, and spin. There is no need for a law stating they must be identical, because they literally are the same thing. The hypothesis, while stunning, faces serious practical limitations. For it to work, the number of electrons and positrons in the universe must be perfectly balanced or off by exactly one. Our observations suggest there is a vast excess of matter over antimatter, meaning there are far more electrons than positrons. This imbalance is difficult to reconcile with a single particle that must switch directions an equal number of times. Furthermore, the idea struggles to incorporate other particles like quarks or neutrinos into the same scheme. Wheeler himself did not necessarily believe it was a true description of reality. He offered it as a profound exercise in radical thought, a reminder that the most elegant, unified answers often lie in questioning our most basic assumptions, like the belief that two identical things must be two separate things. It stands as a monument to the power of a playful, audacious idea to stretch our imagination to its limits, showing that sometimes to understand the many, we must dare to consider the one. The elegant simplicity of a single electron weaving through time leads us to a quantum interpretation where every event is a negotiation between past and future. Theory 40, the transactional interpretation, proposes that quantum particles do not exist in lonely isolation. Instead, they engage in a conversation across time, a handshake that finalizes reality. This radical view, developed by physicist John Cramer, begins with the mathematical waves described by quantum pioneer Erwin Schrödinger. These waves, Kramer noted, have two mathematically valid solutions. One is a wave moving forward in time, which he called the offer wave. The other is a wave moving backward in time, the confirmation wave. In this interpretation, every quantum event starts with an emitter, like an atom or a particle gun, sending out an offer wave. This wave travels forward, spreading out through all possible paths, exploring every potential outcome. It eventually reaches absorbers like a detector screen or another atom. Those absorbers, in response, send confirmation waves backward in time, echoing along the paths of the offer wave. The reality we observe, the specific location where a particle is detected, is determined by a resonant handshake, a kind of standing wave formed when a forward-moving offer wave and a backward-moving confirmation wave perfectly reinforce each other. The strength of this handshake determines the probability of that particular outcome. This elegantly explains the most baffling quantum experiments. Take the classic double slit. A single electron is emitted. Its offer wave travels forward, passing through both slits, creating an interference pattern of possibilities on the far screen. All potential detection points on the screen send confirmation waves back in time, but only one point, chosen at random, weighted by probability, achieves a resonant handshake strong enough to become real. That handshake retroactively confirms the electron's entire path, including its passage through both slits, explaining the interference pattern even for a single particle. There is no mysterious collapse caused by a conscious observer. The collapse is the completion of the transaction, the moment the handshake is sealed across time. The price for this clarity, however, is accepting retrocausality, the idea that the future can influence the past. The confirmation wave from the absorber travels backward to select which possibility becomes solidified. From our linear perspective, the particle's path seems set when we detect it, but in the transactional view, the detection event is what finalized the path all along. It is a cosmic form of destiny where the ending helps write the beginning. This transforms quantum mechanics from a story of random chance into a story of cosmic agreement, where every event, from the decay of an atom to the click of a detector, is a timeless pact between what was and what will be. But if every quantum event is a handshake across time, it implies a kind of predetermined harmony. This brings us to a theory so radical it questions not just particles but the experimenters themselves. Theory 41, superdeterminism, is a controversial, almost heretical interpretation of quantum mechanics. It dares to propose that the universe is not just deterministic, but that every single choice, including a scientist's decision about what to measure, was locked into place at the dawn of time. This idea was born to solve the most stubborn puzzle in quantum physics, the violation of Bell's inequalities. These are a set of mathematical rules that test whether the universe obeys local realism, the common-sense notion that objects are only influenced by their immediate surroundings and that they have definite properties even when we are not looking. Countless experiments have shown that entangled particles violate these rules. They seem to coordinate their states instantly, no matter the distance, implying either spooky action at a distance or that properties are not real until measured. Superdeterminism offers a third, unsettling path. It suggests the experiments themselves are flawed, not in their execution but in a hidden assumption. Bell's theorem assumes that experimenters have complete freedom to choose their measurement settings independently of the particles they are studying. Superdeterminism rejects this. It proposes that the particle states and the experimenter's decisions are not independent. They were both determined long ago by the initial conditions of the Big Bang. The entangled particles and the scientists at their consoles are all part of a single, unbroken causal chain stretching back to the beginning. From this perspective, there is no faster-than-light signaling. The particles behave the way they do because the entire experimental setup, including which button the human presses, was preordained to produce a correlated result that only looks like spooky action. It is a cosmic conspiracy of initial conditions where everything is perfectly choreographed to give the illusion of quantum randomness and non-locality, while preserving a completely local, deterministic reality underneath. The philosophical implications are profound and for many deeply uncomfortable. It strips away not just quantum randomness but the very idea of free will, at least in any meaningful sense. Your choice to watch this video, the scientist's choice to run an experiment at a specific angle, were all written into the cosmic script 14 billion years ago. You are following a path laid down when the first particles cooled from the fire of creation. This is why many physicists are profoundly reluctant to embrace superdeterminism, despite its elegant solution to the entanglement puzzle. It feels like a surrender, an abandonment of the scientific method's core tenet that experimenters can make free, independent choices to test nature. If that freedom is an illusion, then the entire edifice of experimental science is built on a shaky foundation. It turns every discovery into a predetermined revelation, and every scientist into an actor reading lines from a script they did not write. The theory stands as a stark reminder that our quest to understand reality may force us to confront truths that are logically consistent but psychologically alien, where the cosmos is not a playground of possibility, but a frozen, magnificent sculpture, and we are simply the dust that has learned to trace its contours. Superdeterminism paints a cosmos of absolute predestination, but there is a different kind of cosmic script, one written not in initial conditions but in the very geometry of a point of no return. Theory 42, the black hole universe or Schwarzschild cosmology, presents a mathematical mirror so perfect it is terrifying. The equations that describe the unchanging interior of an eternal black hole are identical to the equations that describe an expanding, homogeneous universe. This is not a loose analogy, it is a precise one-to-one mapping hidden within Einstein's field equations. To step inside this idea, picture the simplest kind of black hole, a Schwarzschild black hole with no spin and no electric charge. From the outside, we see the event horizon, a spherical boundary from which nothing returns. But if you could cross that horizon, what would the interior be like? The mathematics reveals a stunning landscape. Inside, the roles of space and time swap. The radial direction, the path toward the central singularity, becomes time-like. That means moving toward the center is not like walking through space. It is like moving forward through time, and it is unavoidable. Every particle, every photon is swept inexorably toward the final crunch. Meanwhile, what was the time coordinate outside becomes a spatial coordinate inside. This means that as you fall, you would experience the universe around you not as static but as expanding. The space perpendicular to your fall stretches and grows. In this inverted realm, the central singularity is not a point in space you can point to. It is a moment in the future, a final moment of infinite density that every infalling observer will reach, just as every observer in our universe will reach the future. The mathematics show this interior is a cosmology, a homogeneous, isotropic, and expanding universe with the singularity playing the role of a big crunch in its future. This mirror is so exact it forces a dizzying question. Could our own expanding universe, with its big bang in the past, be the interior of a black hole existing in some larger parent universe? Are we not the product of a singular beginning, but the interior experience of a gravitational collapse that happened somewhere else? The similarities are provocative. Both models feature a horizon. Our cosmic horizon is the limit from which light has had time to reach us since the Big Bang. A black hole has its event horizon. Both mark a boundary of information. Both models contain a singularity, one in our past, one in our future, and both describe a cosmos that is dynamic and evolving. Yet the differences are equally stark. Our universe is not heading toward a big crunch. It is accelerating outward, likely toward a heat death. The black hole interior, in its pure Schwarzschild form, is destined for a catastrophic collapse. Our universe is also filled with complex structure galaxies, stars, planets, while the idealized black hole interior is perfectly smooth and featureless. So, is this a literal truth or a profound analogy? For it to be literal, our universe would need to be embedded in a higher dimensional bulk, as in brain cosmology, where our three-dimensional space is the interior of a black hole's event horizon in that bulk. The acceleration of our expansion would then require an explanation within that higher dimensional physics, perhaps from the dynamics of the parent universe. Most cosmologists view the black hole universe model not as a literal description of our reality, but as an invaluable mathematical insight. It is a clue that the physics of the very large and the very small of cosmology and black holes are deeply intertwined, two sides of the same relativistic coin. It teaches us that the concepts of beginning and end, of inside and outside, are not absolute, but depend on your perspective within the geometry. You might be living in a golden age of cosmic expansion, or you might be in the final, falling moments of a collapse that began an eternity ago. The equations cannot tell you which story is yours. They only show that, in the silent grammar of space-time, both stories are written with the same words. The profound mirror of the black hole universe emerges from a geometry of stunning symmetry. But what if the ultimate symmetry lies not in space-time, but in the abstract realm of pure mathematics? This brings us to Theory 43, the Octonians and Exceptional Physics, a quest to find the universe's blueprint not in particles or strings, but in the most beautiful and alien numbers imaginable. Our familiar world is built on the real numbers, the line of decimals that measure distance and time. For centuries, mathematicians have discovered that by adding new, imaginary dimensions, they can create richer number systems. The complex numbers, with their imaginary unit I, give us a two-dimensional plane essential for quantum mechanics. Then come the quaternions, a four-dimensional system that perfectly describes rotations in three-dimensional space, used in computer graphics and spacecraft guidance. But the chain continues to something truly exotic, the octonians. These are an eight-dimensional number system so strange they defy our basic intuition. They are non-associative, meaning that how you group numbers in an equation changes the answer. If multiplying a times b and then multiplying by c gives a different result than multiplying a times the product of b and c, you have entered the bizarre world of octonians. Alongside these numbers stand the exceptional Lie groups labeled E6, E7, and the grandest of all, E8. These are not groups of people, but families of symmetries, intricate patterns of rotation and transformation in abstract, high-dimensional spaces. They are the rare jewels of mathematics, appearing almost by accident, with a perfection and complexity that seems too elegant to be meaningless. Some physicists believe these exceptional mathematical structures are not just beautiful abstractions, but the actual source code of physical reality. The most famous and controversial attempt to prove this was by physicist Sir Garrett Lissy, who in 2007 proposed an exceptionally simple theory of everything. His audacious idea was to map all known elementary particles and their interactions, from quarks and electrons to photons and gluons, onto the geometry of the largest exceptional group, E8. Imagine a perfect, intricate snowflake with 248 symmetries. Lissy proposed that each point and line in this abstract E8 snowflake corresponds to a specific particle or force in our universe. The electron, the neutrino, the Higgs boson, all would be mere vibrations or manifestations of this single, sublime geometric object. The gravitational force and the other fundamental forces would unify as different facets of the same crystal. The appeal is overwhelming. It promises a universe born from pure mathematical beauty, where the seemingly random zoo of particles is revealed as a necessary part of a perfect pattern. It resonates with the ancient Pythagorean dream that reality is, at its heart, number and harmony. The theory is breathtakingly economical, requiring no extra dimensions beyond our familiar four, and deriving everything from the intrinsic properties of E8. Yet, for all its elegance, the path from mathematical beauty to physical reality is fraught with immense challenges. The primary criticism is testability. To move from a compelling correspondence to a real physical theory, it must make new, precise predictions that can be checked by experiment, such as forecasting the mass of undiscovered particles or detailing exactly how gravity emerges from the pattern. So far, turning the E8 map into a working, predictive framework has proven extraordinarily difficult. The mathematics is so complex and unfamiliar that even defining a clear path to calculation is a monumental task. Furthermore, the theory, in its initial form, struggled to incorporate some key features of the standard model of particle physics in a fully consistent way. Critics argue it may be a beautiful coincidence, a case of seeing familiar shapes in a complex mathematical cloud, rather than a true description of nature's engine. Despite these hurdles, the pursuit of exceptional physics endures. It represents a profound philosophical stance that the universe is ultimately comprehensible because it is mathematical, and that the most exquisite mathematics we have discovered must in some deep way mirror the cosmos. It is a gamble on elegance, a belief that the human sense of beauty is a reliable guide to truth. When we look at the night sky, we are not just seeing points of light, but perhaps the shadow of an 8-dimensional crystal of unimaginable symmetry, a silent, perfect shape from which all forces, all matter, and the very stage of spacetime itself unfold. The universe may not be expanding into emptiness, but solidifying into shape. Theory 44, the crystallizing universe, proposes that cosmic evolution is not just a story of things moving apart, but of reality itself undergoing a profound phase transition, like a supercooled liquid suddenly freezing into a structured solid. This idea reframes the entire history of the cosmos, from the fiery, symmetric chaos of the Big Bang to the intricate web of galaxies we see today, as a slow, majestic process of crystallization. In the first unimaginably hot moments, the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces were unified, a single, featureless ocean of potential. As the universe expanded and cooled, it crossed critical temperature thresholds. At each threshold, a symmetry broke, like water choosing a specific crystal structure as it freezes. The unified force fractured into the distinct forces we know today. Spacetime itself may have transitioned from a seething, quantum foam into the smooth, 4-dimensional continuum we inhabit. But in any crystallization process, defects are inevitable. Picture a tray of water freezing into ice. As ice crystals grow from different points and meet, their grids don't always align perfectly. Where they clash, you get cracks, dislocations, or trapped bubbles, flaws in the perfect lattice. In the crystallizing universe, similar cosmic defects could have formed as the structure of spacetime solidified. These one-dimensional cracks or two-dimensional sheets, frozen into the fabric of reality as it cooled, might be far more than imperfections. They could be the seeds of everything. Some theories suggest that the most stable of these defects, called cosmic strings, could have acted as gravitational scaffolding, pulling matter together to form the first galaxies. Others propose that certain topological defects, quirks in the geometry of fields that permeate space, could themselves be dark matter. These defects would not be made of particles, but are knots of energy in the very fields that define reality, massive and invisible, woven into the crystal of spacetime. This transforms our understanding of cosmic evolution. The formation of stars and galaxies is not just gravity pulling on gas, but the natural outgrowth of a universe seeking order, its structure emerging as it cools, much like frost forming intricate patterns on a windowpane. The increasing complexity we see, from simple hydrogen clouds to spiral galaxies and planetary systems, mirrors the increasing order of a material moving from a liquid to a solid state. The silence of space is not the silence of emptiness, but the quiet hum of a cosmic lattice settling into its final, stable form, with every galaxy a glittering facet in a crystal still growing in the dark. The crystalline structure of the cosmos suggests a universe built for stability, a system that resists falling into chaos. This drive for preservation finds a startling echo in the most advanced problem-solving of our own time. Theory 45 proposes that the universe itself might function as a quantum error-correcting code. This is not a metaphor about cosmic balance, but a precise mathematical hypothesis emerging from the frontier where quantum gravity meets quantum computing. It suggests that the very geometry of spacetime, its seamless continuity, is not a given. It is actively maintained by a vast, hidden protocol that protects information from corruption, much like the codes that safeguard data on a fragile quantum computer. To grasp this, consider a simple error-correcting code in a classic computer. When you send a message, noise can flip a 1 to a 0, corrupting the information. To protect it, you don't just send the raw data. You add redundancy, spreading the information across multiple bits in a clever pattern. If a few bits get flipped by local noise, the overall pattern allows you to reconstruct the original message perfectly. The information is not stored in one vulnerable place. It is distributed or encoded across the entire system. The radical proposal from quantum gravity is that spacetime does the same thing. The information that defines the geometry of a region of space is not localized in that region. It is stored somewhere else in the quantum entanglement between that region and other, distant parts of the universe. The smooth, continuous space we experience is the decoded, error-corrected output of this hidden quantum data. This idea finds its most concrete form in studies of a special kind of curved spacetime called anti-de Sitter space. While not our universe, its mathematical properties provide a pristine laboratory for thought. Here, physicists discovered a powerful duality, a dictionary translating problems in quantum gravity within the space into problems of quantum entanglement on its lower dimensional boundary. In this map, a volume of space in the interior corresponds to a specific pattern of entanglement on the boundary. Crucially, if you corrupt or remove a small piece of the boundary data, the corresponding region in the interior does not simply vanish. It becomes fuzzy, ill-defined, but the overall geometry remains coherent. The interior is protected from small, local errors on the boundary because its information is distributed non-locally across the entire boundary system. The volume of space is robust because it is built from a web of shared secrets. This transforms our understanding of what space is. A single point in the cosmos is not an independent entity. Its location, its very existence, is defined by its relationships, its entanglement with every other point. An error, like a quantum fluctuation threatening to tear a hole in reality, is constantly being detected and corrected by this cosmic code. The fabric of spacetime is not a passive stage, but an active, dynamic computation, a continuous process of checking and preserving the integrity of quantum information. It suggests that the universe's most fundamental job is not to exist, but to remember, to maintain consistency against the relentless noise of quantum probability. The silence of the void, then, is not empty. It is the sound of a flawless calculation running in the background, an eternal, distributed process ensuring that here remains here and now remains now against all odds. The silent, flawless calculation preserving space might also be weaving the very thread of time itself. Theory 46, the temporal landscape, asks us to consider that time is not a universal river flowing at a constant rate from past to future. It could be a local weather pattern, an emergent phenomenon that varies from place to place, or even a grand illusion that crystallizes from a timeless foundation. Our deepest theories already whisper that time is not absolute. In relativity, time slows near massive objects and speeds up in empty space, but these are distortions of a single timeline. The temporal landscape imagines something far more radical than the arrow of time, the relentless direction from order to disorder. might itself be a contingent feature, not a cosmic law. In the first moments after the Big Bang, the universe was in a state of extraordinarily low entropy, a condition of profound order. This is the ultimate puzzle. Why did the universe start in such a special, organized state? One compelling answer is that it didn't. From a God's eye view outside our spacetime, the cosmos might be timeless. What we experience as the flow of time from a low entropy past to a high entropy future could be our perspective from within a single slice of a much larger static structure. In this block universe, past, present, and future all exist eternally. Our conscious journey from one moment to the next is like a spotlight moving across the frames of a completed film. The feeling of time's flow is the experience of the spotlight, not a property of the film itself, but could different parts of the film run in opposite directions? Some cosmological models allow for the mind-bending possibility that other regions of the multiverse, or even distant parts of our own cosmos beyond the horizon, could have an arrow of time pointing opposite to ours. In such a region, the universe would appear to contract from a state of high entropy toward a state of low entropy, culminating in a big crunch that looks, from their perspective, like a big bang. To them, we are the ones living backward. They would remember the future and anticipate the past. Cups would assemble from shattered fragments on the floor and leap into their hands. Light would emanate from their eyes to illuminate objects. Such a reality is mathematically possible, though utterly alien to every intuition we possess. This leads to the profound idea of time emerging from timelessness. At the level of quantum gravity, where spacetime dissolves into a foaming sea of possibilities, the concepts of before and after may have no meaning. Time, like space, could be a collective property that condenses as the universe cools and grows large, much like the crystalline structure of ice emerging from liquid water. In this primordial quantum realm, every possible history exists in superposition. The universe we experience is one consistent thread pulled from this timeless tapestry, a story that coheres into a sequence of cause and effect. And what of time crystals, those bizarre quantum systems that tick in their ground state? While the ones we create in labs are microscopic, the principle hints that time itself could have a periodic, structured nature on cosmic scales. Could the expansion and contraction of a cyclic universe be the ultimate time crystal, a heartbeat of reality with a period of trillions of years? The implications touch the core of our existence. If time is not fundamental, then free will and destiny must be re-examined within a block where all choices are already made, yet felt as real. If time's arrow is local, then the heat-death of our universe might not be the final word for the whole of reality. Other domains might be experiencing their own dawns, their own flows, in directions we cannot fathom. The silence of the cosmos is not just a spatial quiet, but a temporal one. We are listening in a universe that may be still from a higher perspective, and our entire history is just a single, beautiful note held in an eternal chord. The silent ticking of cosmic time may have left behind relics from its first moments, objects so dense they could be hiding in plain sight. Theory 47 proposes that the mysterious dark matter holding galaxies together is not a sea of exotic particles, but a swarm of ancient primordial black holes. This idea resurrects a decades-old hypothesis, suggesting that in the chaotic furnace of the universe's first second, regions of space with slightly higher density could have collapsed directly into black holes. Unlike the stellar black holes we know, born from the death of massive stars, these would have formed from the raw pressure of the cosmos itself, and they could span a breathtaking range of masses. Some might be as small as an asteroid weighing less than a mountain. Others could be as massive as 1,000 suns, all forged before the first star ever ignited. For years, this idea seemed to fall out of favor as searches for these objects came up empty, and the particle dark matter paradigm took hold. But the cosmos has a way of reviving old mysteries with new data. The key challenge is finding them. A black hole drifting alone in the dark is nearly invisible, but astronomers have two powerful methods to hunt them. The first is gravitational microlensing. If a primordial black hole passes directly between us and a distant star, its gravity will act as a lens, bending and magnifying the star's light for a brief period. We would see the star temporarily brighten in a very specific, symmetric way. Surveys like the optical gravitational lensing experiment have monitored millions of stars for decades, looking for these telltale flashes. Their results have placed tight constraints, ruling out the possibility that all dark matter is made of black holes in the mass range of a large planet to about 1/10 of our Sun's mass. They cannot be everywhere in that size. The second, more dramatic method comes from listening to the ripples in spacetime itself. The LIGO and Virgo gravitational wave observatories have detected the mergers of black holes with masses that were surprisingly large, some tens of times the mass of our Sun. Where did these hefty black holes come from? While they could be the remains of unusual stars, their masses and the properties of their mergers have renewed serious interest in the primordial black hole hypothesis. Could some of these be ancient relics from the beginning, pairing up and colliding over cosmic time? If a significant portion of dark matter were tied up in black holes of roughly this mass range, it could explain both the missing mass in galaxies and the source of these puzzling gravitational wave signals. The beauty of this idea is its stark simplicity. It requires no new physics beyond general relativity and the hot, dense conditions of the early universe. It suggests that the dark matter problem might not be a call for undiscovered particles, but a cosmic archaeology project, a hunt for the first structures to ever form black holes that have been weaving the galactic web from the shadows since before light itself was free. The hunt for ancient black holes is a search for cosmic ghosts, but sometimes the universe offers a signal that seems to shout. Theory 48, the alien megastructure hypothesis, centers on a single, baffling star over 1,000 light-years away in the constellation Cygnus. Known as KIC 8462852 or Tabby star, it behaves like nothing else in the galaxy. Discovered by citizen scientists in the Kepler telescope data, this ordinary-looking star undergoes dramatic, irregular dips in brightness, sometimes dimming by up to 22%. These are not the clean, periodic shadows of an orbiting planet. They are deep, jagged, and chaotic, as if something enormous and uneven is passing in front of the star, blocking its light in a pattern that never repeats. The most extraordinary and least likely explanation proposed was that we might be witnessing the construction of a Dyson sphere. This is not a solid shell, but a vast swarm of energy collecting satellites or panels, orbiting a star to harness nearly all of its radiant power. It is the theoretical hallmark of a Type II civilization on the Kardashev scale, a society that has mastered the energy output of its entire star system. A partially built, lopsided swarm could perfectly explain the star's erratic dimming, casting strange, geometric shadows as it rotates. The idea ignited global imagination, but science demands rigor. Astronomers have chased down every natural explanation. The leading candidate is dust, but not ordinary interstellar dust. The star's light dims more at some colors than others, pointing to clouds of extremely fine, microscopic dust grains, perhaps from the breakup of a giant comet or a family of exocomets in a highly elliptical orbit. Other possibilities include a huge, deformed planet with colossal rings, or the aftermath of a planetary collision leaving behind a massive debris field. Each natural model has its own challenges in fully explaining the bizarre light curves. The true value of Tabby's star lies not in proving aliens, but in proving our own methodology. It became a case study in how to investigate an anomaly without jumping to conclusions. It showed that the universe is still full of natural phenomena we have never seen before, processes that can mimic the signatures of intelligence. The search for such technosignatures, however, is now a legitimate and growing branch of astrobiology. We are no longer just listening for radio signals. We are scanning the skies with telescopes, looking for unnatural patterns in starlight that could betray the presence of a civilization advanced enough to reshape its star system. We might look for the waste heat of a Dyson swarm glowing in infrared, or the unnatural chemical signatures of industrial pollution in an exoplanet's atmosphere. Tabby's star taught us to look harder, to be skeptical, but also to keep our minds open to the staggering possibility that we might one day find a signal that refuses all natural explanations. It reminds us that the greatest discovery in history would not be a message, but an artifact, a silent, cosmic-scale construction project glimpsed across the void, forcing us to confront the reality that we are not the only architects in the universe. The search for alien artifacts forces us to define what reality even is, a question quantum mechanics has made profoundly personal. But what if our shared, solid world emerges not from a single observer, but from a kind of natural selection? Theory 49, Quantum Darwinism, offers a stunning answer to the deepest puzzle of all: how the fuzzy, probabilistic quantum realm gives rise to the single, objective reality we all agree on. The problem is this: in the quantum domain, particles exist in superpositions, a haze of many possible states at once. Yet when we look at a chair, we all see it in one definite place. How does this transition from many possibilities to one agreed-upon fact happen? The traditional Copenhagen interpretation says a conscious observer causes the wave function to collapse, but this makes reality seem subjective, dependent on being seen. Quantum Darwinism proposes a more elegant, automatic mechanism. It suggests that the environment itself acts as a constant, unconscious observer, and it is ruthlessly selective about what it records. Imagine a quantum system like a newly emitted photon. It starts in a delicate superposition, but it does not exist in isolation. It is immediately bombarded by its environment, by countless photons of background radiation, air molecules, and stray electromagnetic fields. These environmental particles constantly interact with the system, probing it, trying to copy information about its state. Here is the key: only certain special quantum states of the system are robust enough to survive this onslaught. They are like hardy seeds that can be scattered and copied without being destroyed. These are called pointer states. When an environmental particle, say a stray photon, bounces off the system, it can reliably imprint and carry away information about these pointer states. That one photon then interacts with others, which interact with more, creating multiple redundant copies of that specific information. This process is the Darwinian part. The environment selectively proliferates or breeds countless copies of information about the stable pointer states, while information about the fragile, superposed states gets scrambled and lost into irrecoverable noise. So, what does this mean for you looking at a chair? The chair is made of atoms, which are quantum systems. Their stable pointer states correspond to definite positions in space. The light bouncing off the chair, the air molecules touching it, the dust on its surface, all these environmental factors are constantly making trillions of copies of the information that the chair is here, in this specific location. You, as an observer, do not cause a collapse. You simply tap into a tiny fraction of this vast, pre-existing sea of copied information. You catch a few of the countless photons that have already been imprinted with the message, chair here. Another person in the room taps into a different subset of the same widely broadcast information. Because you are both accessing redundant copies of the same stable data, you agree on what you see. Consensus reality is not a miracle, it is a consequence of information replication. The objective world is the one described by the pointer states that have been massively duplicated and made available to any observer who cares to look. This elegantly bridges the quantum classical divide without invoking consciousness. The transition from quantum to classical is not a sudden event, but a process of information spreading, of certain states being chosen by the environment for their durability and then broadcast far and wide. It suggests that what we perceive as solid and real is simply what has won the evolutionary battle for survival in the noisy marketplace of quantum information. Its story copied so many times that it becomes the official history of the universe. Quantum Darwinism shows how a shared world emerges from countless copies, but what if that shared world is the only thing that exists and the underlying reality is a phantom? Our journey concludes with Theory 50, the most radical proposition of all. It suggests the universe has no single underlying reality waiting to be discovered. There is no objective, observer-independent world prior to measurement. This is not a philosophical musing, but a conclusion forced by the mathematics of quantum mechanics itself through a property called contextuality. Contextuality means the answers you get from nature depend on the specific questions you choose to ask, and even the order in which you ask them. It is as if you are interviewing a cosmic witness who does not have a fixed story, but constructs one on the spot based on your line of questioning. You cannot assume the witness has a secret, true version of events hidden in their mind. The answers are the event. This shatters the classical intuition that particles have definite properties like position and momentum, like a car having a definite speed and location even when no one is looking. Quantum contextuality proves that such a hidden, complete set of properties is mathematically impossible. The properties do not exist until the specific act of measurement calls them into being. This leads to the cubist interpretation, short for quantum Bayesianism. In this view, the quantum state, the mathematical object that describes a system, is not a picture of reality itself. It is a tool. Specifically, it is a catalog of an agent's personal beliefs, a set of betting odds about what that agent will experience in future experiments. For a cubist, when a scientist assigns a quantum state to an electron, they are not describing the electron's objective condition. They are encoding their own expectations based on past experience about what will happen when they interact with it. Another scientist with different background information or a different experimental setup might assign a different quantum state to the same electron. And both would be correct because the state belongs to the observer, not the thing observed. This transforms the universe from a monolithic object into a tapestry of perspectives. There is no grand, single tapestry woven from absolute threads. Instead, each conscious agent weaves their own local piece of the tapestry based on their unique interactions and history. When our experiences strongly agree, as they do in the classical world, it is not because we are all looking at the same underlying reality. It is because our personal belief structures, shaped by the relentless copying of information from the environment, have converged on the same robust predictions. We are not sharing a single dream, we are having billions of highly consistent, overlapping dreams. The implications are as profound as they are humbling. It means the search for the ultimate theory of everything, a single equation that describes the universe from the outside, may be fundamentally misguided. There is no outside view, there are only inside perspectives, each valid for the agent who holds it. The cosmos becomes a collaborative story, told from a near infinite number of points of view, with no author and no final draft. The silence of space is not the silence of an empty stage, but the quiet between countless simultaneous performances, each one real only to the observer who lives it. This is where our journey through 50 mind-bending theories leaves us, not with a definitive answer, but with a breathtaking question. If reality is not a solid thing we discover, but a relationship we co-create through every observation and every choice, then what story will you tell with your next glance at the stars? This voyage through 50 cosmic riddles has taken us from the possibility that we live in a simulation to the haunting silence of a dark forest universe. We have explored black holes that might be gateways to other realities, questioned if time is an illusion, and wondered if consciousness itself is woven into the fabric of space. Each theory, from the elegant mathematics of octonions to the ghostly pull of the dark flow, represents a different crack in the facade of ordinary reality, a place where our most fundamental assumptions break down. They are not just ideas about space, but profound investigations into existence, identity, and the very limits of knowledge. The common thread binding them all is a beautiful, relentless human urge to look beyond the horizon of the known and ask what lies beyond. This quest inevitably turns inward, forcing us to redefine what is real, what is time, and what it means to be a tiny, conscious speck in an incomprehensibly vast and mysterious cosmos. The universe is the greatest story ever told, and we are both its readers and its authors, deciphering clues written in starlight and quantum equations. So the next time you find yourself under a clear night sky, remember this journey. Let the silence speak to you. Let the darkness feel alive with possibility. Keep looking up, keep questioning, and never lose the wonder that first made you stare at the stars. The adventure is far from over. Which of these 50 theories bends your mind the most? Share your favorite cosmic mystery in the comments below, and if you crave more journeys to the edge of understanding, subscribe and join us as we continue to explore the final frontier.